Philosopher Chris Payne. I'm a black hole. And being a black hole, I will just watch some videos on YouTube. YouTube is a website with videos. YouTube. This would be a good one.
How does a space probe like Voyager 2, which was launched in 1977, visit the 4 outer planets and travel over 17 billion kilometres over a space of 40 years with almost next to nothing in the way of fuel? By the time Voyager 2 had reached Neptune, it had swung by Jupiter, Saturn and Uranus, travelled 7 billion kilometres and was still within 100 kilometres of its target, and all with mid-1970s technology. In the movies, spacecraft just seem to fly where they want and get there in no time at all. But in our version of reality, it's somewhat more complicated and takes much, much longer to get around.
Right, so you're not...
Can you imagine Spock
because I'm
saying
here.
to Kirk, "We've just passed Pluto, almost home. Only 9 years to go." Just in case you missed the relevance of that, it took 9 years for the New Horizons probe to get from Earth to Pluto, a distance of about 5 billion kilometres, and that was one of our fastest spacecraft. It might seem like an impossible task, but when you know how space and physics works, it becomes a set of procedures.
It's very interesting.
Science fact
They said something
instead
about
of
the
science
bald
fiction. And key
guy
to all
is
of
a
this
joke
is
in
knowing
one of my
how
last
gravity
streams.
works and how it affects not only you and me, but also everything in the universe. The German mathematician Johann Kepler first worked out the laws of planetary motion 400 years ago.
Right.
Isaac Newton then used these as a basis for Newton's laws of motion and the creation of classical mechanics, the means by which we can predict the movement of everything in the solar system and beyond, including planets, comets, asteroids and spacecraft, with incredible accuracy.
Really?
Newton's first law states that an object at rest or travelling in a straight line will stay that way unless a force acts upon it. A rock, for example, on the ground won't move by itself unless something else picks it up or pushes it along.
A force? No, not something
If
else.
that same rock were in space and moving in a straight line, it will not change its speed or direction of travel unless an external force acts upon it.
External?
In space, there is always a force acting on a moving body, and that force is gravity, be it from the sun, a planet, or even another rock.
What force is
with
gravity?
mass
It's always acting
exerts
is
a
one of them?
gravitational force. The larger the mass, the larger the force.
There's
The
more
other component to a moving object is its speed.
than gravity?
Newton's second law states that an object's speed will change when a force
Force
is
is
applied
generated
to
with
it.
speed
This is also
changes.
reversible, so a force
is that why I'm
is
talking
generated
right now?
when its speed changes.
Don't smile.
This is also the reason why an asteroid travelling at 17 kilometres per second and hitting the Earth can be so devastating. It can release a huge amount of kinetic energy with the sudden change in its velocity.
Okay.
If you fire a projectile on Earth, parallel to the ground, it will eventually fall under the influence of gravity back to the ground. If you fire your projectile fast enough and it maintains that speed, it's still travelling in a straight line. However, Earth's gravity continuously pulls on it.
Yeah.
And when the curvature of its trajectory matches that of the Earth,
Okay.
it's now said to be in orbit around the Earth. In other words,
Right.
the
I
force
orbit the
of a
Earth.
projectile
Well,
trying
I'm
to
a
go in a
black
straight
hole.
line is matched by that of gravity pulling it back to Earth. This is how satellites and space stations stay in orbit. But they are also affected by the tiny amount of drag of the very thin atmosphere high above the Earth.
Like me.
This slows them down, and the force keeping them in their orbits becomes smaller. The
What am I
balance
shrinking
between
into?
this and gravity gradually tips towards gravity as
Okay.
it pulls them down further.
What gravity?
As they
Down
get
where?
lower, the
Down?
atmospheric drag becomes even greater, reducing the speed even more. Without a periodic boost in speed to increase their orbit, they will eventually come back to Earth.
Right, or else
If,
we just
however,
don't
a
talk about
spacecraft
anything.
increases its speed,
Right, so
the
if I keep
orbit will
talking
become
more
larger
and
and more elliptical. But it will always return to pass through the point where the speed was originally boosted. If the speed of our craft is increased enough, then it will escape the pull of Earth's gravity and enter an orbit around the Sun. With an approaching planet in what's called an opportunity, we can get the orbit of our spacecraft to intersect the orbit of a planet in a method known as the Hohmann transfer approach, which is one of the most common ways to get from one moving body to another, although there are now more efficient but much longer ways like the low thrust transfer method and the interplanetary transport network method. Once there, our spacecraft can either enter into an orbit around the planet, or we can use the planet's gravity to slingshot around it, or use gravity assist as it's known, and increase the craft's speed relative to the Sun.
Right.
Gravity assist works by using a planet's gravity to pull on our spacecraft as it flies close by, and can be used to increase or decrease a spacecraft's speed, and as such make its orbit larger or smaller and change its direction of travel. If our craft is flying in the direction of motion of that of the planet, then it will speed up. If it flies in an opposing direction, then it will decrease its speed. Depending upon how it approaches the planet, its course can be changed dramatically and can even leave travelling in the opposite direction. But there is no such thing as a free lunch. And in order to obey the law of conservation of energy, what energy our craft gains,
no such thing as a free lunch.
Lose. When the Voyagers used Jupiter to increase their speed to get to Saturn, Jupiter's orbit around the Sun slowed, but only by about 1 foot per trillion years. We can use this gravity assist method to move from planet to planet, further and further away, increasing our craft speed as we go until it reaches escape velocity, the point where it will be travelling fast enough to escape the pull of the Sun and leave the solar system, just like Voyager 1 has already done. But the Sun's gravity will still pull on the craft and slow it down. In fact, the Sun's gravitational effect extends out about 2.5 light years. And it will take Voyager travelling at over 60,000 kilometres per hour, 40,000 years, to reach the point where the Sun's gravity no longer dominates.
Why would it do
Newton's third law states that every action has an equal and opposite reaction. Basically, the thrust from an engine pushing backwards moves the craft forwards. Some people think that the thrust of a rocket pushes against the ground or the atmosphere, and thus it's impossible for them to work in space. This is clearly not the case, as our rockets and thrusters don't stop working once they are in space, when there is nothing for them to push against. We use this thrust to increase or decrease speed and as such change our spacecraft's orbit, as well as move it in its X and Y planes with thrusters to orientate its antenna with Earth or point its cameras towards a target. Once we know how gravity affects our spacecraft and that we can use it to move from planet to planet, the next thing we need is an accurate model of the solar system. This will show us where the planets will be in relation not only to the Sun but also to each other and
accurate. I think we need to agree.
Comets and asteroids. This model is created from the planetary ephemeris, which is like a timetable for all the major bodies in the solar system and gives their positions relative to the Sun for any given time, both in the past and the future. This data has been built up over centuries, with the first ones being created by the Babylonians as far back as 1200 BC. By using celestial mechanics, it's possible to calculate ephemeris for several centuries into the future. Because space missions last for years or even decades like the Voyager ones, it would be impossible to plan missions without knowing where the planets would be in the years ahead. However, these ephemerides are not perfect due to the gravitational effect of unknown asteroids and maybe an as yet unknown planet X far beyond Pluto. NASA has updated its ephemerides almost every year for the last 20 years as new data has come to light. So, knowing how our spacecraft will move in space and the position of the planets well into the future, This allows navigators to plot a course for our spacecraft with incredible accuracy. This can be seen with the Voyager missions. They used planetary ephemeris to find a once-in-a-175-year alignment in the planets Jupiter, Saturn, Uranus and Neptune. This was discovered by Gary Flandro in 1964 whilst working at JPL, and allowed the planners to come up with the Grand Tour. This would allow one spacecraft to visit all 4 planets by using gravity assist and cut the mission time from 40 years to less than 10, if they launched in 1977. The original Grand Tour was to include Pluto, but due to funding limitations it was left out. But Pluto was visited by the New Horizons probe in 2015. Voyager 2 was the first to set off in 1977 on the Grand Tour of the 4 outer planets, and eventually travelled out in the plane of the solar system. This same technique of gravity assist has since been used on the Galileo, Cassini and the New Horizons missions. Voyager 1 launched 3 weeks after Voyager 2 on a quicker route to visit Jupiter and Saturn and do a flyby of Saturn's moon, Titan. But this would then put it on an upward trajectory and out of the plane of the solar system to interstellar space. On its way out, it was turned around so its camera could face back to Earth and take one last set of photos.
So this is me.
These were the farthest images of the solar system ever taken, and one of them captured Earth's place in it, covering just 0.12 pixels in size. In the middle of a lens flare, the famous pale blue dot, as Carl Sagan called it, was taken 6.4 billion kilometers away, looking down at a 32-degree angle onto the solar system. Now we have a plan, we still need something to guide our spacecraft along its planned trajectory. For this, they use an inertial navigation system. Basically, this is a highly accurate system of gyroscopes, accelerometers, and other sensors that can detect movement of a craft in any direction in space. Using this information, the navigators can work out if the craft is on course. However, inertial navigation systems are mechanical devices and as such suffer from what is known as integration drift, tiny errors in the gyroscopes and sensors. This is compounded over time because they calculate their position as they move along from the last previously calculated position. So the longer they go, the more the errors build up. The error in a good system is less than 1.1 kilometers per hour. So if a journey to Mars lasted 8 months, which would be 5,760 hours, then the error would be about 6,300 kilometers by the time it reached Mars. Far too much when you have to enter an orbit with an accuracy of just a few kilometers. To compensate for the integration drift, another fixed reference system is needed, and this is the stars. Just as marine navigators used a sextant to work out their position, spacecraft use optical sensors and cameras to determine their position and reset the inertial navigation systems. On the Apollo missions, the crew used a space sextant to correct the drift on the onboard navigation system. On the Voyager probes, they used a star tracker that could look for a very bright guide star, which in Voyager's case was Canopus. It also had a sun sensor that could be used in conjunction with a radio signal from Earth. Newer spacecraft have more sophisticated systems which use cameras to look for known objects like planets and even comets and asteroids, as well as the target itself. Even with the best planned course, things will vary along the way. Other forces can also affect a craft deep in space. The solar wind, for example, the flow of charged particles from the sun can, over time, gradually change the course of a spacecraft and has to be corrected for. And timing is everything. Our spacecraft must arrive at particular points in space along the journey within a very small window of time. Travelling at 30 kilometers per second and approaching a planet to use its gravity to swing by and change course, if you are out by more than a few minutes or so, it could mean the difference between being sucked into the planet by its gravity or undershooting the planned course. To communicate and work out the distance and speed of a craft, NASA uses the Deep Space Network. This is a network of radio telescopes spread around the world so that at least one will be in contact with the spacecraft at all times. By sending a radio signal to the craft
Neat.
and having it return the signal, and
Yes,
using
I
the
just
Doppler
did.
effect and a highly accurate atomic clock,
Okay.
the slight difference between the two signals can be used to calculate its distance from Earth to within 3 meters
Wow.
and its speed to within 180 millimeters per hour. Combining all this information, we are now able to send space probes with incredible accuracy, so much so that we can now
And,
land
yeah,
on a
for adults.
comet, as we did with the Rosetta probe and its Philae lander,
Rosetta Stone.
and to take close-up pictures of Pluto within a 2-hour time window, 9 years after launch and 5 billion kilometers away, and when we only had 1/3 of Pluto's orbit mapped. 5 spacecraft have now achieved escape velocity using these methods we've spoken about, and are now the farthest objects created by man.
Wow.
Pioneer 10, 11, Voyagers
Voyagers
1 and 2, and New Horizons.
Wow.
It's incredible to
New
think that all
Horizons,
of this
'cause
was
I'm the
done
black
based
hole
on
phosphor
theories that were
participant.
developed hundreds of years
Sorry,
ago
bald
by
guy.
observation only, and the desire to figure out how the heavens worked long before we even thought it was possible to get into space, let
twitched
alone
hard
use
there.
gravity as our main engines. The ability to work out the orbits of the planets is a key fundamental in planning any space missions that we will be doing for the foreseeable future. And it's something that you can do yourself with the help of the guys over at Brilliant.org. Brilliant is a problem-solving website that
Still?
allows you to learn by solving real-world, or in this case, outer space problems. They have a complete section dedicated to gravitational physics, covering not only Newtonian gravity but also
I know, I did
Keplerian
this, and I
orbits,
got a
where you
headache.
can work out how to plot a course to Mars using the Hohmann transfer method, just as if you were sending your own craft to explore the solar system.
I am.
You can also test your abilities
This is
with
my
the
craft.
classical mechanics
And
section,
I'm telling you, my
the
drives already
discipline
did
that
this.
Newton helped create that underpins our ability to predict the actions of any object in space, and something that
So you can't
any
predict me.
budding space navigator has to know. To help support us here at Curious Droid and to learn more about Brilliant, just click on the link to brilliant.org/Curious Droid and sign up for free.
I know I'm brilliant.
As a
Thank you.
special bonus for Curious Droid viewers,
Appreciate that. Thank you. I'm Brian Green, co-founder with Tracy, and I also want to welcome you to day 4 of the 2016 World Science Festival. The
Hey,
program tonight on gravitational waves. It's a timely
Hey,
program.
Brian.
I trust you all heard the announcement on February 11th, or you read about it.
Hey,
the
Brian.
first direct detection of gravitational waves. Amazing, amazing discovery. And we have here tonight a group of the very individuals who made this discovery possible. I'm going to bring them out in just a little bit, but just a few words at the outset. You know, this discovery, just to put it in
the
context, it's the kind of achievement that happens maybe a few times a century in fundamental science. I mean, we
Me?
were
Cool.
thrilled some years ago for the discovery of the Higgs boson. something that was
Awesome.
searched for
Thank
for
you.
a very long period of time and finally was definitively discovered at CERN. Great discovery. This ranks on par with that kind of experimental
Are you tired?
observational achievement. And the other side of the story that will come out in the conversation here tonight is that whereas for the Higgs boson, just about everybody was convinced that the experiments would succeed. I mean, most people who were following closely the search for the Higgs boson were saying, well, if it's not found, that's the craziness. I mean, this has got to work out. The theory says it. All of the circumstantial evidence suggests that the particle is out there, and indeed it was found.
Cool.
Now, with
Thank you,
gravitational
you found
waves,
it.
as we'll see, there was never really any doubt after, well, I don't know, call it 1950, 1960, that these ripples in the fabric of space were a real feature of Einstein's general theory of relativity. But there definitely was controversy as to whether we would ever have the capacity to catch one of these waves. And we'll hear about why in just a moment. But what this means is it takes a certain kind of internal fortitude.
It does.
It takes a certain kind of vision. It takes a certain kind of stubbornness. It takes a certain kind of independence of spirit to devote your life to this kind of project.
Brian.
And our hats are off to the individuals. They now number roughly 1,000 who made this discovery possible. Okay, a little bit of background before I bring the panelists on stage, just to set the stage scientifically, right? So we're all more or less familiar by this stage of the game that Albert Einstein gave us a new theory of gravity in 1915, the general theory of relativity. The Newtonian picture that we all learned in high school simply spoke about objects pulling on each other through space with some sort of force that was described mathematically, but whose mechanism of exerting its influence was not articulated.
What do you mean?
Albert Einstein
is yours?
Came along and articulated the way that this force is communicated. And just to give a picture of it, the first little clip here, it goes like this. Objects, you can bring the lights down a little if you will, like the sun or the planets, they warp the environment of space and time, and it's these warps and curves in space that are able to cause other objects to move along peculiar trajectories if you weren't aware of this picture.
Peculiar.
The metaphor that we love to use, it's imperfect to be sure, but if you think about space and time as sort of like a trampoline, you put some heavy object in the middle of it, it warps the surface, and then if you roll a marble, the marble goes into orbit, much like a planet would.
Thinking about it.
Much the same way the sun warps the environment, and then the planets go into the orbital trajectories that we're familiar with.
I mean, this is how I was told.
Okay, so Einstein gives this very beautiful new description of gravity in 1915, and then the question, of course, is
he wrote a paper
correct?
on it, I think. I'm pretty sure.
And indeed, there were very quickly two pieces of evidence that sealed the deal. The first was an explanation of a puzzle having to do with the motion of the planet Mercury.
Communication
According to
planet. My
Newtonian
communication
gravity,
planet
the
is
planet
zinging
should
around.
just trace out the same orbit year after year after year, but observation showed that the orbit was actually shifting a little bit.
Yeah, because we shift on two poles,
Nobody could give a
buddy.
good explanation of this.
Two axes
Einstein comes along and uses his new approach, this new picture of gravity, uses the equations of general relativity,
I'm a black hole, phosphor, Chris Payne.
spot-on predict
Brian.
this so-called precession of the perihelion of Mercury.
Perihelion.
Now, that was kind of a post-diction explaining a puzzle that was already known observationally, but then he was able to go further and make a prediction for something that had not yet been seen. And indeed, that had to do with the bending of light by the sun. So if you have a distant star, it sends light toward the Earth, goes in a nice trajectory of that sort. But then later on, if the Earth is on the other side of the sun, and you now consider that starlight, according to Einstein's new picture, it's going to go in a curved trajectory as it goes through the curved environment surrounding the sun.
Curved?
And that has the effect of making the position of the star in the sky shift. Einstein was able to use the equations of general relativity to calculate
Shift.
the angle.
Appear
And
or
it was
measure
just
shift
a
or
few years later that teams of astronomers went out and measured the angle between those two positions, taking photographic plates during a solar
Okay,
eclipse, so
for
you
what?
could see those distant stars. Compare it with photographic plates taken 6 months earlier,
Yep.
and indeed the data with a little bit of massaging, a little bit of forethought, a little bit of actually knowing the answer in this particular case.
Sorry.
Seemed to show that Einstein's ideas were correct. Now, since then,
Einstein.
these experiments have been done over and over. There's no doubt any longer that Einstein's theory is correct.
Well, it's
Now,
relevant.
Einstein then went further. And as we'll discuss here tonight,
Sorry, buddy. Sorry, Brian.
he wrote a paper
You can
in
hear me.
1916
Okay, no shit.
in which he basically says, he didn't use quite this language, but basically
Right,
says
what's this
mathematically
dark stuff?
that if space is sort of like a trampoline and it can warp and curve,
Yep.
well, if you start to tap the trampoline, disturb the trampoline, you'll send ripples going along the trampoline. Those ripples, taking away the metaphor, would be ripples in the fabric of space. And
Right.
that's what gravitational waves are. Now, it's a very interesting story
Not
that we'll get
time,
into a little bit in just a moment
but just
with
space.
our panelists. Einstein himself, he writes this paper in
Hello.
1916, actually made
Einstein.
a little mistake. That may be a kind of weird concept, Einstein making a mistake, and doing
mistake to-
calculations in
To
relativity.
whose standards?
But relativity is hard.
Wow. Sorry, Brian.
And Einstein was the first one who was actually working on these calculations. So he was making what we would
He's
now
the
call
first one?
mistakes of a beginner.
How do you know the first
Novice
one?
mistakes. But he was the guy who was blazing the trail.
Oh,
so
he
it makes
blazing the
perfect
trail,
sense that he
right.
might have made those kinds of errors.
Phosphor,
Anyway,
Chris
he
Payne.
corrects the error in 1918, but
Wow.
then he continues to have a really interesting relationship with this idea.
Right.
Thinks it's not quite right, writes
No
later
way.
papers that suggest that it's not right. Bottom line is, others come along, develop a very beautiful systematic framework for avoiding the pitfalls that Einstein fell into, and
Yeah.
people are absolutely certain
No
that
way.
these things are real. And what would that mean? It would mean that if you disturb the fabric of space, you should get these gravitational waves, these ripples, and the prototypical example might be something like this. Rapidly orbiting neutron stars or black holes sending out this march of gravitational waves. And
March?
as we'll discuss here tonight,
A
what would that
march?
mean for somebody in the wake of these waves? The object would be stretched or squeezed according to the math. Now, I want to emphasize one thing.
What? Whoa.
This is not to scale. And that is a big deal. Because when you actually do these calculations,
really thought
that
it
we'll
was?
discuss, the stretching and the squeezing is so small that it is an enormous challenge.
You
to
really
detect
thought
these
it was?
gravitational waves, and that is what the LIGO team has done. All right, so now let's get into
LIGO team.
the actual discussion. I'm going to bring our panelists on, and let us begin with Ray Weiss of MIT. Is one of the creators of LIGO. He first proposed a large-scale interferometer back in 1972, and he has been the scientific and engineering leader ever since. All right, next up, Barry Barish. Many people say that Barry Barish of Caltech saved LIGO at
Barry
the time
Barish.
it transitioned into big science and
It
built
saved
two huge
LIGO.
detectors in Louisiana and Washington State. He joined LIGO in 1994 and
Wow.
was director from 1997 to 2005. Welcome.
Wow.
Next up, Nergis Malvavala. Got
Nergis.
it. I'm so proud of
Hello.
myself. Of MIT.
Nergis
Is an
Malvavala.
astrophysicist who was MacArthur
Very
Genius
cool, man.
Award winner for her work on LIGO in 2010. She got her PhD
Wow,
from
very good for
MIT
you,
in
Mer. I
1997,
apologize.
postdoc at Caltech from 97 to 2002, and then joined the faculty
Instinct.
of MIT. Welcome. Next
Wow.
up, Franz Pretorius, who is a professor
Franz
of physics at
Pretorius.
Princeton University. His primary
These are
field of
good for
research is
individual names.
general relativity, specializing in numerical solutions to Einstein's equations, and as we will see, a vital part of this discovery. Finally, David Shoemaker, who is director of the MIT LIGO lab and was the team leader of Advanced LIGO, which spent many years upgrading the technology at the observatories and led to the historic detection even before Advanced LIGO was officially launched.
Very
Welcome.
interesting. Hello.
Okay,
You have
thank
long
you
hair.
all for joining us here tonight.
What up, Brian?
Let's just get into it. So,
Yeah.
in the description of this discovery, many have called it, one of the great achievements of our age. And because of that, we're thrilled to note that a filmmaker who has generously given us some footage has been following you all around for a little while, Les Gutman. And we are going to begin each section of tonight's discussion with a little video clip from a documentary that he is making just to sort of set the scene for each of the discussions. Let's, if you will, run the first clip.
Wow.
Take the entire universe, count every photon that's coming from every star, and add it all up. That's how much energy was released by this event.
It's the most energetic astrophysical object ever observed since the Big Bang.
Whoa.
You worry that in any complicated experiment like this, that you may have made a discovery, but you're not sure that the discovery is really true.
Whoa.
And I mean, there's many situations in my life where that's happened.
We've been through a whole series
Wow.
of exercises to figure out what this was, and many of them, underlying them, are self-doubt. We're like, could we have caused this by our own ignorance, or anything from accidents to, to malpractice?
There's this wonderful thing that goes around, is there some evil genius that has laid this into us? This evil genius gets to be
Laid
more
what?
and more complicated and more skilled as you delve into this in a deeper and deeper way.
And what is this
So it's not just one evil genius, it's a multiple group of evil geniuses.
Every check we've done
Who
has kind of
and where?
come back
What?
saying, no, this really came from some astrophysical origin, we believe. I mean, nothing in the instrument that we found so far could have done this, and nothing that we have found so far indicates that it could have been some intentional or accidental or malicious injection. And so then you start almost believing it, and that's pretty cool.
I think the remarkable thing is not so much that we
Believing
saw a
what?
gravitational wave. I mean, that's remarkable enough, but it isn't the real centerpiece of this whole discovery. That centerpiece is the fact that we saw a particular source that nature seems to have given us. It's the best source we could have imagined. It's the source that says Einstein is right on every goddamn detail almost. In other words, this is a source that doesn't require any other physics
Wow.
than general relativity. Let's think of that.
So we're gonna
General relativity?
unpack the discovery in a number of stages. But let me just begin. I
Einstein in
recall
general relativity.
last fall, rumors started circulating all around that you all had seen a gravitational wave, and that was probably, I started to hear about this October, November, something of that sort. First off, what was your feeling when these rumors started to get out there? You guys had not announced yet, but yet there was this growing anticipation. Was that exciting? Was it irritating?
Of what?
Irritating.
Why?
Anticipation of
You want
what?
to make the case, when you do something like this, you want to make the case right, and we weren't ready to make it right. So
Right,
it's very
I agree.
irritating and worrying.
Yeah.
Because if it did come out, and we had to defend it, we weren't ready.
I think there was a real
Barry, so-
process. Oh, sorry. There's a real process for us as well, from the time we saw the first signal to believing that it really was
Believing?
of astrophysical origin and not something in the detector. And
I mean, was your initial thought that it was not real?
Very much so.
Yeah.
Let me say something about
And you're not being all modest now,
No,
like, it's
no.
really how you
What?
felt.
No, let me tell you what
Yeah,
I
please.
mean, all of us, I think everybody here, and if you disagree with me, raise your hand, but however,
That's absolutely true.
it looked just too good. That was the thing. No, I'm very
Yeah.
serious about it. I mean, here we've gone to...
You mean if someone was going to fake a signal, this
well,
is
we'll
what they
get to
would
faking
do?
it in a second, but let's
Yeah,
just say what it
yeah.
looked like when you first saw it.
I mean, we've gone through a lot of stages expecting signals that would be just marginal.
Yeah.
And we had gone and made lovely algorithms to be able to look at the data very carefully.
Signal?
And here was this thing that came on in the morning, and you didn't have to do much filtering. I mean, you could look at it with your eye without a lot of computing. It's almost nothing more than if you had a radio and you had a bass in the treble control. You did a little adjusting of it.
Phosphor Chris Payne?
See it a little better. And that's all we had to do to see this waveform. That was the thing that made us all suspicious. It was an absolutely beautiful waveform.
Why are you suspicious, bro?
Paraphernalia that we had developed.
Now, suspicions of what?
That, yeah, well, I can tell you, we had every one of us had some thought, and I wish you guys would speak up.
I think
Yeah.
we of course, injections. It's something we regularly do. We inject signals that look just like the astrophysical sources that we're looking for to ensure that the pipelines can actually recover the signals correctly.
Now, does everybody know about those injections? Are they secret? What is
Most of them, yes, but in our initial LIGO experience, and we planned also for advanced LIGO to make blind injections, ones which were unknown to all but 1 or 2 or 3 persons who would push the buttons and set the system in motion. And I actually knew a lot about that right at that moment because I was working with the team.
But let me just ask you, so if one of those,
Cool,
injections
dude.
is made, is the point that if someone on the team doesn't recognize that signal, they get fired? Is that basically what it's about?
Certainly, if a pipeline that should have detected that signal does not detect it, then questions are asked.
Yes.
And what are you
All right,
guys
so go
going to
on with
ask
what you're
each
saying
other?
about the
But good, so
injection.
just at that time, we were trying to demonstrate that we had the technical capability in this brand new instrument, Advanced LIGO, to make injections successfully. And we were actually having a lot of technical trouble. And I knew that the night
Yeah, I mean,
before,
who are
someone
you
was
guys?
trying out some code that might have been a way to get around the problems that we were having. And so my initial thought was, oh, good, they finally succeeded in making an injection. I went to look in the logbook, and it wasn't logged there. So that's when the question really started to come to me that it might be a true signal.
Philosopher
And so
Chris
what
Payne.
stage was the apparatus?
I'm a black hole.
It had not actually
Apparatus.
officially been turned on, right? It was still in a very much of a testing
Right,
stage.
we had just, go ahead, Ray. Oh, okay. We just started an engineering run. We regularly hold these runs, which are not to do astrophysical observation, but to run the instrument and leave it alone for a week or a couple of weeks and try and understand if we know how the noise behavior is, see if it's stable, see if it stays locked, see if the operators know how to get it into and out of lock successfully. And we had just started the engineering run that was to immediately precede the observing run. And we were 2 days into it when we woke up to this. So,
And now I heard that
I'm
somebody
not
on
trying
the
to
team,
precede
maybe
you.
even on the panel had suggested to not have the detector actually on for various work that you were doing in order to set it up for the official use of
Someone
the.
was going to do a test that might have knocked it off and went home and went to sleep instead.
A lot of stories.
Homer?
A lot of stories like that we almost missed it because.
Yeah.
I mean, for example, I was in Livingston and we had a problem I wanted to fix.
Yes.
And I was told I told people it would take 2 weeks to fix it. And I was there the Thursday before the Monday, okay, when the thing happened.
Right.
So if they had given me permission to do that, we would have missed it.
Right.
So, and there are other stories, like the one that Barry just said. You know,
Now, just want to, when you say missed,
Thursday and
again,
Monday?
we're going to go into the details of the device in the conversation that goes
Philosopher
forward.
Chris
but
Payne, right?
if I
Today's
understand
Wednesday,
correctly, so this was
December
an event that happened a long,
30th,
long
2020,
time ago,
on
right?
Monday.
Very, very far away, more than 1 billion light years away, right? So this collision of 2 black holes, which is what this is, sets off this tidal wave
I'm
that
in a quantum
ripples
tunnel
through
right now.
space
Sorry,
and
buddy.
time. And so you're saying that it's been traveling toward the Earth for like 1.3 billion years, and it just so happens
That I'm that guy.
just as it's rolling by
Philosopher-
Earth, you've
rolling
got this
by
device that's
Earth.
just turned on and catches it.
Yeah.
Sorry, you're right.
Yeah.
Philosopher Chris Payne. Wow, no shit. Good for you guys. This is awesome.
So Franz, you're not on the LIGO team, even though your work is vital to the successes
Wow.
we will see. So what was your feeling when you began to hear these rumors?
Well, yes, I'm not on LIGO, and actually, the way that I first heard these rumors is people would come up to me and say, well, have you heard these rumors? And I felt like I was actually one of the last people to actually hear the rumor. So it was like about 2 months later.
Rumors are whoa.
There's someone within LIGO leaked it. I won't break their confidence and say who it was. But
It's interesting stuff, though.
They sent me this email
guess.
with this waveform.
Email.
And the hair went up on the back of my neck, and just like it shivers through my skin. It was like holy bleep, these things are actually out there. It was the most
Hey, buddy.
astonishing thing to see that.
Yeah. Philosopher
then
Chris
you realize,
Payne.
I mean, I've been studying black holes for 20 years.
No,
since
I'm a
I-
black hole.
Relativity is a fascinating theory.
Black holes where? Tell me what you know.
This is
Who are
my
you?
field, but still, from a scientific perspective, it's not just that they're beautiful, remarkable, astonishing predictions of a theory. I think as scientists, we want there, especially with something which is as astonishing as a black hole, we want an equivalent, astonishing level of evidence. And so in some sense, I was hoping
Astonishing.
that they existed, but I was sort of agnostic, and then seeing that it was a real revelation.
Wow.
The second thought that went through
Good
my
for you.
mind is that, no, this can't be right. This looks just like those first simulations. Someone did a blind injection and they stupidly just took the most obvious thing that was available.
No.
I mean, were you concerned about
Wow.
sabotage? Was that also part of the thinking?
One of the things we spent time on was...
Who's
to put this-
sabotage?
Luckily, it's two very independent laboratories. So to make this happen simultaneously limits the options, but it's something that we worked very hard to do.
And they are in
God is
the
all your
locations
lab.
of
The
the laboratories.
locations are in Louisiana and in
Just
Washington
looking away.
State.
Sorry, I don't mean to
So
make you
This
uncomfortable.
had to happen within a few microseconds in both and look alike. That was very difficult, but we
Right.
still...
Both
really
in
want-
look alike.
And can I ask
So you do
another-
feel the
I don't
same.
know if this is a sensitive
Brian,
question
help me
or
out.
not, but there was
Whoa, you
an
took a deep breath
announcement
there.
by
Right.
a different team
By what team?
using
Who?
a completely different approach.
Okay,
looking
right.
For a related kind of signal, but not the same one. BICEP2.
Yes.
Which found evidence of gravitational waves indirectly through its effect on the cosmic microwave background radiation. Some of you may have been here when we had a discussion of this sort right when that announcement was made, but before it
This
became
one is
clear
named- Oh, shit, is this
that
an
was
announcement?
actually probably not the right interpretation of the data. So that was sort of a premature
No, that's totally the right
announcement
one.
that actually got a lot of people irritated, not because the announcement was of something that turned out ultimately not to be the correct description, but people felt that they'd really jumped the gun.
Okay,
This
right.
team had kind of gone to a press conference as opposed to going through the more traditional channels. Did that influence your thinking at all?
No, I mean, look, I know a lot about that experiment.
Yes.
So let me say something positive.
Yes,
instead of
please.
Something negative.
Okay.
It's very important. That team that reported that experiment had made a dramatic improvement in the technology of the detection of the polarization, which is how the electric field points in the cosmic background radiation.
Yes.
Prior experiments had been 20 times worse
Wow.
than any experiment that those guys did.
Yes.
So
That I
was
did?
a
No shit.
dramatic improvement. And what they did,
Cool.
they didn't have enough channels. In
Right.
other words, they made an interpretation. They did, I think, an honest
Channels
job.
meaning frequencies.
Did-
Oh.
I'll
Yes.
get to what it
Yeah.
is in a
Yeah.
second. But they didn't
Whoa.
have enough channels at the South Pole where they did the experiment.
Did not
What they
have
saw
enough.
was a particular pattern in the sky of the polarization vectors. And that's, if people ask what that is, but there's a pattern that the particular gravitational waves
In the
would
sky,
make in the
polarization.
plasma of the primeval plasma, and that would then cause these waves that come from, electromagnetic waves, that come from the early Big Bang plasma to have a particular pattern to the polarization, swirly patterns.
Yes.
And they saw those swirly patterns.
Yes.
The trouble is that there are other things in nature that make those, and that's what you were referring to.
Of course.
And
Yeah.
they knew that.
We're
They
fungal.
knew that. That wasn't that they were surprised by it. They knew that dust would cause that, dust in our own galaxy, and also electrons in our own galaxy that are in magnetic fields. Those are
Higgs
synchrotron.
boson.
So both ends of what they were looking at, but they didn't have enough detectors of different frequencies to see that. So they made a judgment based on maps that they had. I think they were honest.
Yes.
Okay? And they made a
Thank you.
judgment that the dust couldn't be as bad as to make what they saw.
Sure.
And
their
Einstein-
paper
Einstein-
makes that.
And the
that
paper
clear,
makes
yes.
that very clear. Now,
Yeah.
where did they make a mistake? They made at least one mistake.
You guys
I
did.
almost forgive them for that mistake. I don't feel so bad as some others. It is, I mean, the dramatic development that in their own technology to be able to do this. And what they did then is they assumed that the dust wasn't bad enough to do it, and they published it without going to peer review.
Yeah.
See, and the group
Peer
was
review.
too small. That's the real problem. They all had agreed among each other. One of my students was on that team, and they had discussed this a lot internally, and they all together decided to take this gamble. So what
Wow.
happened is that then they needed a bigger group to look at that, and that's why peer review is a very good thing to do.
Right.
And
Is
that
it
peer review
good?
exposed the fact that there was a good chance that maybe it was dust that they hadn't gotten.
Right.
And,
Yeah.
and that's where it stands
World
now. It's still
review.
not, they haven't retracted,
Yep.
you know, but.
No, what they saw is what they saw.
Yeah, they saw
But
what
the
they saw,
interpret-
right, yeah,
Absolutely.
yeah.
But back to your original
Yeah.
question, does
No.
that kind of thing worry
I'm a
us?
black
Yes.
hole.
Yes.
I think the
Thoughts
answer
for
is
Chris Bain.
definitively less. Yes. We
Yeah.
didn't want to come out with the wrong result. Nobody does.
Yep.
This particular thing breaks all the rules. If you work in a laboratory and you do something and you see something,
So I break all the
you do
rules.
it better, you do all the checks.
No,
This
I
comes
don't.
by in a quarter of a second. It's gone.
Yep, there you go.
Right?
Sorry,
So we
buddy.
only have what we have to look at.
Yep.
We know you talked about, before we came on stage, the CERN discovery of the Higgs. They spent a huge amount of money to have two experiments, so one can check the other.
Yep.
Wow.
It's a way physics does things and gets the right answer. We can't do that here, so this had to be extreme. And I've seen experiments that seem convincing based on one thing, and they're wrong. So I was very, very pessimistic and worried. and
Wow,
so
no
forth.
way.
This just was so powerful, we had to.
Following up on that, you know, I think an interesting question just to get out in the open here is, so Einstein, I mean, take us through the history of this. Einstein writes his paper predicting gravitational waves back 1916, 1918, interesting.
Okay.
As I described, he had a sort of complicated relationship with gravitational waves, might we say. But
Einstein
why
did?
can't we do this in the laboratory? Why is it that we're only looking for, you know, colliding black holes or neutron stars? Why is it possible that we could have done this in a way that was closer to an experiment that we could replicate and do over and over again?
Sure, so you're asking, could we build a source of gravitational waves in a laboratory? And the answer is emphatically no. And it's really embedded in something that we all learn pretty early in our careers, that gravity is a very weak force. And so what the ingredients that
Yep.
you need for making gravitational waves has so much mass compactified that a laboratory source is not possible. You can imagine taking, an example that we love to use is take a dumbbell,
Yep.
but make it the most ridiculous dumbbell you ever could think of, which is it's a rod that's 1 meter long, and you put a 1-ton mass on each end, and then you spin it at 1,000 times per second, and then you go stand a couple of 100 meters away from it and ask how strong will the radiation be, and it is such a ridiculously small number. It's like 10 to the minus 42. It's so
a
small that I'm
ridiculous
almost
question.
reluctant to say, right? And so. So no, it's
Reluctant
not
to
possible.
say.
And that's why we have to go out into the universe and look for objects that have
Is that
enormous
because
amount of
9/11
mass. The
twisted my
black holes we
view
saw
of
have
George Bush and the
30 times
presidency?
the mass of our sun. And
The
they're,
mass of me is
you
right
know,
here. I can tell
at
you how
the
much I
time
weigh. You
that
want me to
they're,
hop on
they're
a scale?
getting close to colliding, they're 150 kilometers, and those are the conditions.
That we now know that we've got to look out
Very good
into the
description.
cosmos and look at extreme astrophysical bodies, neutron stars, black holes. Now the question is, how do we get a handle on what we expect to see from Einstein's general theory of relativity? And Franz,
Well,
that's where I
I
want
can't
to
tell you
move
the
on
event
to
horizon. I'm a
the
black hole.
numerical side of the story, which it's interesting. I have not read all press accounts by any means, but I haven't seen that side of the story given as much attention as it might deserve. As I think
Mine?
most everyone
okay
would
with
agree. Yeah, you agree with that, don't you?
Now you
So I
laughing?
just want to spend a little bit of time on numerical relativity is what the name
Why?
of the subject is.
Why would you
And
laugh?
first, we're going to begin again with a little clip that'll set up the conversation, and then I'd like you to help us take us
Right.
through why computers and numerical methods are so essential. So we can run this next clip.
No
if you will.
way.
So numerical relativity, the first part, the word numerical is because we use computing techniques. So what happens is that
Deidre, is she related to a
the
homeboy
theory
at
of
the end?
gravity that Albert Einstein came up with others about 100 years ago, last year, is extremely complicated equations, or set of equations. And they're very nonlinear. And that means that if you had
Mallinear?
one black hole, you could solve it analytically. But if I have two black holes, they don't add together. That's a linear theory. So to solve for two, I have to solve the full Einstein equations with all of its nonlinearities. And that takes computational techniques. In fact, it took us until 2005 to solve it. And this was Franz Pretorius from Princeton.
We have to use
You solved
numerical
it.
relativity simulations, which basically simulate the Einstein equations on a computer, and we build what we call templates that are used in the model search in
I don't
LIGO.
believe you.
The model search that found the event used on the order of 200,000 templates. Also, we use waveform models not only to detect the signal, but also to infer the parameters, the properties, because all the information
Parameters.
about the source are imprinted in the waveform. It's like a fingerprint in the waveform.
So you're mentioned in there as the guy, right, who made this all
Yeah.
possible. So why
Philosopher Chris Payne.
do we need numerical methods? Why do we need computers?
Well, perhaps I can just also take a step back and just say a little bit about, the kind of observatory that LIGO is.
Yes.
Right, it's
Okay.
not like a telescope.
So you
where
guys are really
you
doing
focus,
this right now?
look at a
Holy
certain area of the
fuck.
sky, you focus, you look, you form an image, you see what's going on. It's in some sense
Holy
a one-dimensional
shit.
seismometer in some sense. We're listening to a sound.
No,
and
you're
so
not. You're listening to my
you get a
inner
gravitational wave, It's
violation.
a gravitational wave, but it's a series of wiggles. What does that mean? It's not giving you an image of the source. So
Whoa.
we need solutions to the Einstein equations for various possible sources, black hole
Okay.
collisions, that tell us what those wiggles look like, and so we can
I think
identify what's
they've
going
already.
on.
Wow.
So that's
Is
one
this
thing.
all
We need
opinion-based?
Solutions to the field equations.
And the field
Ooh,
equations,
K
by the
Payne
way,
8.0.
have just magically appeared behind you.
Yeah, it did.
And look how simple they are.
Philosopher
Well,
Chris
that's
Payne.
actually part of the question that I wanted to
No way.
explore. I mean, it looks simple, but we physicists have this way of hiding complexity behind the symbols. And for this part, actually, I just want to take us through, because sometimes in these programs, it is meant for the general person who just has an interest, but we'd like to sometimes do a little bit of the math. And if you don't like math, you can shut this part off. But
Okay.
let's just do a little tag team here.
I
So
only
this
did
is
pick
the
out-
form of the Einstein equations, and if you're doing it a little bit more precisely, it has a few more symbols in it if you're
Yep.
not using the
There's
natural
one more thing
units
you're
that
missing,
allow
buddy.
us to set certain terms to one.
In my
But even
opinions.
that, if we go a little bit further,
Yep.
is
Sorry,
hiding
bud.
this. So this is actually a
And now you brought it
more
up.
complete way of expressing the equations if we're now going to unpack the meaning of that first symbol, G mu nu. But then you look
Yep.
at that and you say, well, wait, what do all those individual symbols mean?
Unpredictable,
This
man.
is
I'm a
called
black
the
hole.
scalar curvature, and that thing G is called
Sorry,
the
y'all
metric.
here.
And there's this little combination of them that gives you the scalar curvature.
Philosopher
But
Chris
wait,
Payne.
what does that really mean? Well, that's hiding
three,
this
zero,
complexity
zero.
right here, because we have this way of
Yeah,
hiding
yeah.
the summation symbols within what we call the Einstein convention,
No.
using indices that contract in a particular way. So that's what
Convention?
that symbol means. And if you go a little bit further and ask yourself, what is the first term, R mu nu? That's the Ricci tensor.
The
and
Ricci
it's given by this
tensor.
combination of stuff. But what's that new guy on the right-hand side? That's the Riemann curvature tensor. What does that equal
Riemann
to? Well, that's equal to
curvature
this
tensor.
combination.
Whoa.
Where those gammas are known as the Christoffel symbols. And then you
Christoffel
take those, and what are
symbol.
they equal to? Well, they're equal to a particular combination of the metric contract with various derivatives.
Whoa. No, keep
And
going.
all just
Keep
to tell you
going.
that this is
That's not
kind
ending.
of complicated.
How does
And
that
the
end?
goal of the Einstein field equations, what all
Does
of
not
this
solve?
in some sense is about, is understanding
Nope, philosopher
that guy
Chris Payne.
called
I'm a black
G,
hole.
which is the
Jake
metric tensor. And just tell us quickly what that is, and
Richard.
I'll have a little visual that'll take us through that as well.
Wow.
So Einstein's theory is a theory about space and space-time is a geometric structure. And the metric tensor, in some sense, at every point in space-time, it's a generalization of the Pythagorean theorem.
So actually,
Pythagorean
you have not
theorem.
seen this before, but you are following exactly what I hoped you say. Okay. So you said the Pythagorean theorem, so why don't we just put that
I
out
did.
here for the heck of it right now.
Okay,
So you got 2
thanks,
points
Brian.
there, and take us through what you're seeing right here.
Right, so you want to know the distance between 2 points. So now in general relativity,
Oh,
it's
wow.
not the distance between 2 points in space, it's the distance between
What's your name
two
again?
what we call events in space and time. And so what the metric does
Thanks,
for
buddy.
Pythagoras' theorem, we know it's delta x squared plus delta y squared plus
Right,
delta z
we-
squared.
Slow down, I'm
square
trying to click. I'm trying to click and stay up with you. Here we are. There it
sorry.
is. Right.
So that little formula there encodes the geometry of Euclidean
Touche.
space.
Advertisements pop up all the time.
Now, you can also write it in terms of a metric, and it's a relatively simple, straightforward metric.
Hmm.
And what people long before Einstein's time, when they started looking at general geometries of curved surfaces,
Curved.
they would say, well, how do we describe,
Ooh, you got
if we now have a
curved?
surface that's got a complicated curvature, we want to generalize what Pythagoras did. this metric is the convenient mathematical way of doing it.
And here's one just example, just so people who are following the math can go along. Here's a curved shape, if you will, and the distance between the 2 points is no longer just delta x squared plus delta y squared square root, which is what we learned in junior high school, but rather is given by some unusually looking strange combination of delta x squared and delta y squared. And if you curve it a little bit differently, we learned that the distance between those 2 points might be given by this particular combination of delta x squared and delta y squared. And finally, just to get to what you're describing in the general case, we can have combinations that aren't even just delta x squared, delta y squared. We can have cross terms, like on the far right, delta x, delta y. And finally, to get to that object called G, the metric tensor, this is sort of a generalized version of the Pythagorean theorem where you're going to allow the surface to be curved. And that G thing there encodes the geometry that Franz is referring to. And Einstein gives us equations, those complicated equations that we saw before, where you can determine the shape of space-time if you understand the distribution of mass and energy.
I do.
Yeah, exactly right. And then
thank you.
Thank you. Applause for Chris Payne.
And perhaps just another example, a historic example where we might be able to appreciate how complicated those equations are. So the idea is at every point, it's basically a 4x4 matrix. So we need to know over all of space and time. And if we know this metric tensor, we can ask any question about the geometry. Is there an event horizon? What do light rays do? Are there gravitational waves?
Thank you.
So the first solution, the
do?
exact solution, was by Karl Schwarzschild in 1915, within a few months of Einstein publishing equations. And he was able to solve it exactly because he assumed, he said, well, let's look for a spherically symmetric solution. And so the metric simplifies. He found the solution. That turned out to be the first black hole solution. It wasn't known.
So he actually beat Einstein to the punch, right? He found the first solution even before Einstein.
So Einstein couldn't solve his equations exactly. He solved sort of an approximate version to compute the pericenter precession of Mercury. So it's Karl Schwarzschild that found the first exact solution in spherical symmetry. And that was in 1915. Then if you relax symmetries a little bit, so make it something called axisymmetric to look for spinning black holes, it took people almost 40 years. So Roy Kerr in 1963 found the solution for rotating black holes. So I mean, it's not that people weren't looking for them and they weren't trying. It's just things very, very quickly get very complicated. And now if you want to understand the metric for two black holes that are colliding,
philosopher Chris Payne and us.
Every single term is important. And we have absolutely no way of doing it pencil and paper with analytic methods. And thankfully we have computers, which the methods have been developed in the last several decades to solve these kinds of equations using computers.
And what did you do? What was your breakthrough? I mean, when I was a graduate student, people were always talking about numerical relativity and this stumbling block that they couldn't get through. And now people aren't so worried about that stumbling block.
Yeah, so
the Bible?
It's a little technical, so perhaps I can just explain by analogy.
The what book?
Yeah.
So the one thing about it, so those field equations are very complicated.
Field equations are.
But in some sense, they're even more complicated in the sense that a feature of Einstein's equations are
the Constitution?
So this is a geometry of space-time. There's a coordinate system, but you can use any coordinate system you want.
Right.
So for example, a Cartesian coordinate system, a spherical polar coordinate system.
Particle,
so one physical space-time, you can represent it in infinitely many ways.
Yeah.
Every single representation has a different metric tensor, yet they all solve the same Einstein equations. So in some sense, there are infinitely many possibilities for one space-time that comes from these solutions.
Yep.
So that's a feature.
Philosopher Chris Payne.
In some sense, one aspect of the principle of relativity.
Let me talk to you at the end.
The problem then, if you want to say, well, now let's try to solve these equations. So we start with something at an initial time, two black holes that are separated, and now we want to understand how do they collide.
Okay.
If we try to put that on a computer, it's what's called ill-posed. In some sense, the computer doesn't know which one of those infinitely many solutions to solve.
Ill-posed.
So the way you get around this, and this was known for a long time, is, well, you have to first choose your coordinates.
Whoa.
Okay, so we do that, but then the real nasty problem comes. So that's what people did tried to do in the early 90s when it was realized, okay, LIGO is being funded, we need to have these templates, so let's do the numerics. And it was, okay, well, let's do that. We choose our coordinates, we put it on a computer, and things just crashed.
Wow.
We'd start with the two little black holes, they'd go for a little bit, and then the dreaded NaN shows up. Any of you know computers, not a number. The computer's telling us it's not getting a number,
right.
and you can't go beyond that.
Right.
And it took actually people a long time to realize that
computers
because when
are
something
not humans.
crashes, I mean, it could be a bug. You didn't program something right. It's very difficult to really figure out what's going on. And it really took probably a good 10 years, I think, before people realized that there's these things called constraints in the field equations, which are the problem. And so that's one way to think of it is, okay, let's imagine a bowling alley. Okay, so we want to knock down the 10 bowling ball, the bowling pins with our bowling ball. And so we throw the ball down the alley, and let's just say we're not going to fling it into the air, so it's going to go along the bowling track. So one constraint, if you will, is that the bowling ball rolls on the surface. It doesn't jump off the surface. Okay, so it doesn't seem too difficult.
Right.
But now, we're going to be a little bit more careful in that. We want to say, we want to hit the center pin. We want to get all of those 10 pins knocking down. So our constraint is we want that bowling ball to roll right down the center of the alley, not off to one side or the other.
Right.
And in some sense, those are the constraints of the Einstein equations. When we put them on a computer, there are all these other possibilities which aren't solutions to the equations that you can get. There's that one solution that is a solution to the Einstein equations. But what makes the Einstein equations so nefarious, and that's the big struggle, is it's not just a straight bowling track, it's actually convex. And so
Umbrella
the
wells.
path that you have to get it down is sort of at the top of this cylinder. And people actually didn't really realize that was happening. So in some sense, we're starting our simulations, we're starting the two black holes, think of it as this rolling pin, and it's just falling off the side the whole time. I mean, people realized that that really was the issue. Then it was, well, can we somehow, we don't want to change the solution to the Einstein equations, the straight path to the center, but we can fiddle with the equations to change the track on either side. So we can try to bend it upwards, in a sense. And then sort of a huge effort started, in the late 90s to try to find ways of changing the equation such that we can make this a well-posed problem. And so in a very long story, that's hiding a lot of technical issues under the rug. That was sort of the breakthrough, was finally coming up with a way to actually make this thing stable.
And with that, you were then able to calculate numerically with supercomputers, presumably what shape of the wave you would anticipate receiving if certain kinds of processes happen out there in the universe. And I think we've been seeing some of those templates. Now I hear numbers like you had hundreds of thousands of templates. Why so many templates? What are these things that you need so many of them?
What was astonishing about this event, and I think no one expected this, is that you can actually see the waveform directly in the data. So so nature has given us a gift which we didn't even expect something as good as this. What was actually anticipated was that you wouldn't really see such a clear signal. You'd actually just see the noise.
Can you just tell us what we're seeing up there?
Right. So, good to explain that. So the little gray lines, that's essentially the noise in the detector. The blue lines, that's the in-spiral of the black holes. They start out far apart.
Let me pull back. It's time along the horizontal axis, and it's a tenth of a second for every 2 clicks there. And on the vertical axis, it's how much space is being distorted by the passing gravitational wave.
Wow.
And the noise from the instrument isn't actually the space-time jiggling around in length. It's electronic noise, mechanical noise, and so forth and so on from the instrument. So, I'm sorry, go ahead.
Whoa. Thank you for we deal with this every day. It's something we just get way ahead of things. Okay, so as time, so these black holes are orbiting each other. They're emitting gravitational waves. These are the stretching and squeezing of space-time, which is what's being picked up there. These waves carry energy from their binary, and so by conservation of energy, the binary gets tighter. They spiral in closer to each other. They start moving faster. So the frequency increases because they're going faster.
Stephen Hawking, philosopher Chris Payne, Morgan Freeman.
Runaway process, and eventually they
Will Smith,
together.
smaller
And that's when
philosopher
you get
Chris
the very
Payne.
peak in the waveform.
Shiva.
And then so to these two
Philosopher
black
Chris
holes, they
Payne.
smash together. and
Jesus
form
Christ.
This very distorted, rapid
Philosopher Chris
oscillating
Payne.
horizon. And one of the remarkable features of black holes in general relativity is something called the no-hair theorem, which says that any isolated black hole has to be this sort of this perfect object, stationary, doesn't emit gravitational waves, that's represented by this Kerr solution that I mentioned was found in 1963. And so what we're seeing after the peak is what are called the ring down waves. So the black hole is essentially losing its hair. It's shedding all this interesting structure, and it's just settling down to this perfect Kerr shape.
Yes.
So there's this beautiful picture here, and we're going to now, in just a moment, go to the details of the actual detection itself.
Wow,
But
right.
it seems clear from the outside.
Yeah, just cut
that
me off
the
live whenever you need to talk
numerics
to
was
me.
vital to interpreting and believing and being able to pick out the signal from the data. Now the breakthrough that allowed this
Brian.
numerical analysis to go forward happened when? In the mid-90s-ish?
2000.
Now you guys have been building
Allow
this
you guys to go
detector
forward.
for a long time
Do I get credited?
before that. So were you like
You
prescient,
evil
imagining
bastard.
that people would be able to make this breakthrough? I mean, would you have built this device and not have been able to pull out the signal if
Did I build this
somebody
device?
hadn't
God
come
did.
along and pushed the numerical methods?
Luckily, we were too slow. Took us twice as long to do this as we thought it would.
But
Right.
what was your
You guys are
thinking?
too
Just so
slow.
I can get a handle
Sorry,
on it.
Brian.
This was a problem, and it was pushed very hard that we find a solution for,
Hey,
for
Barry.
this particular black hole
Yeah.
question.
I should also
What?
also mention that there are other methods of solving the field equations
Okay.
approximately in different regimes. So when the binaries are far
Regimes.
apart,
Okay,
so they
Franz
sort of in their
Pretorius.
slow early part of the in spiral, there are these analytic methods called post-Newtonian or perturbative methods where you can start getting the beginnings of this chirp. And
Which
I
we'll
think-
come to in just a moment.
Yeah.
But
Let me say something.
Yes, go ahead.
In defense of our ignorance. We were, to us, this business of finding a black hole the first go round was
Yes.
a surprise.
right.
We were thinking, because
Nope,
I'll tell you, we
I'm
could
here.
not figure out, we could not tell each other or tell an agency who was supporting us how many of these things we would find. So
Philosopher
actually, we were
Chris Payne.
thinking of another source entirely, as what we were really designing the apparatus initially. To
And
do.
that you had more of a
And
handle on.
we knew a lot more about
Yes,
this, okay?
okay.
And that was neutron stars, which are, again, things that are of the source of the size
Right.
of the sun, sort of the size of Manhattan Island.
Yep.
Mass of the sun, the size of Manhattan Island. And we traded on the fact that Hulson-Taylor, which is an experiment that won the Nobel Prize back in, I think, 2003. Was it that? Maybe that late, I've forgotten. It was within my life, certainly, okay? And
Mine too.
and what they saw was something which was one of the most elegant experiments I think ever done in astronomy. Was they saw two stars one would be a pulsar. That pulsar is a neutron star that emits pulses that you can see in the radio spectrum.
Yep.
And they noticed that there was a modulation to the pulsar. It was going around at
Yeah.
50. They had pulses.
No, I did. You guys are big names.
Every eighth of a second or something like that.
Que
And
pene
8
por
pence
no.
per second, really, what they saw. And then there was a
Philosopher
modulation.
Chris
to that. Sometimes
Payne.
it would
What
speed up,
you don't
sometimes
know
it
what
would
I
slow
saw.
down.
I'm telling you right
Indicated
now.
That one pulsar was somehow living with another thing around it. And that turned out to be another pulsar, or another
Yeah.
neutron star.
Wow. So you do know about me,
with
and you
that,
know we're
that
living
was
near
sort
each
of
other.
That business and plotting it for time, they began to be realized that these two neutron stars were emitting gravitational waves. It's the only way they could explain the change of
We
the
are
orbits
emitting
that were
gravitational
losing
waves?
energy to gravitational waves. And with that gave an enormous impetus to the
You
field,
keep going
our
on.
field. That, in fact, let me say a little about the early days, because that's sort of what you're alluding to. In the very early days, for example, when Joe Weber began,
But we'll come to
and
in
we'll
just a
come to
moment.
that.
Yeah, but go ahead,
when
yeah.
he was thinking about it, and when people were thinking, what might he see? When he
Joe
did see
Weber.
something, they were thinking of supernova. That was the only thing.
Right.
These are, these stellar implosions that happen once every 100 years in our own
Galaxy,
galaxy.
yeah.
And
Yep.
that was sort of the only thing people could see had enough acceleration, had enough mass that
Yep.
would possibly make a gravitational wave. And that was the beginning of the field, but it turned out to be quite wrong. But the estimates were for that. We still don't really have good estimates for supernova. They're getting better. And so when the neutron star binary was discovered, and people began to see there were binaries of these, that became our goal for detection.
Right.
And the thing that
So let me just so in that particular case,
Yeah.
there was indirect detection of gravitational waves
Right.
by virtue of the in spiral, but you guys wanted to see
That's
the direct.
something else.
Yeah,
That's
right.
it. But I mean,
Yeah.
just say you asked
Yeah.
what was the impetus
Yeah.
for us to continue. Okay.
Yes.
And the impetus was really in all our calculations were
continue.
then done for neutron star binaries.
Gotcha.
And in fact, what we still, when we get to design sensitivity with this detector, we expect to see something like 10, maybe 20 of these a year of neutron star binaries. Okay?
Right.
We're not at design sensitivity. We'll talk about that
Yeah,
later.
sure, we'll get to it in just a
But
moment.
anyway, so it wasn't that the thing that everybody wanted that we should detect black holes, and because I think to me that's the big source to look for. And I remember giving a talk at Cornell. Hans Peter was in the audience at the time, and I told him the story that I just told you. And he said, he pulled me aside later. He said, "No, you're going after the wrong source." He said to me, "Go after black holes." And I said, "Look, tell me how many there are." And he couldn't tell me that.
There's one,
You know,
Philosopher
but
Chris
he's
Payne.
right. I mean, if there are black holes, that's better. There's more mass and stuff like that. So
There's
anyway, in other
one,
words, we
and it's
started the
Philosopher
field
Chris Payne.
with ignorance, there's no doubt. But the idea that there should be gravitational waves coming from some astrophysical sources was the basic idea. We didn't know exactly where, and that was a big controversy in the beginning of the field.
It's okay.
You know, Kip Thorne, who was like one of the visionaries of this thing, did a lot of calculating of different classes of
Kip!
sources. And in fact, got himself into trouble with some of the real experts in this business because they thought he was a little too optimistic. But anyway, look, all the things that he calculated will probably come about, is my guess.
At some point.
At some point.
So before we go on Nurgis, any thoughts on the numerical side of things?
Yes, I just wanted to add something. Franz said something really important that I wanted to emphasize. So, you know, when the black holes or neutron stars are far enough apart, we knew what the waveform there would look like. We also knew what the waveform would look like once they'd crashed and a single object was forming. The part we didn't know, and that was so important in the breakthrough, was what happens when they're really close together and about to collide. So in some sense, if we hadn't made that breakthrough, you can think of it as we would have had all of those bumps and squiggles. We would have had a little gap in the middle of that time series where we wouldn't know exactly what was going on. And it's a pretty important region because that's where the amplitude is the biggest. So there was ignorance, but we also had a handle on enough of it that we thought we could go on.
Yeah, good point, Nurgis.
All right, so let's, go ahead,
One
please.
last one on
Yeah.
this point, though, as the real...
Enough of
just
your
an
guys'
experimenter, I have to
ignorance.
say, we built two instruments. If we see the same signal in these two widely separated instruments, but one which we can't explain by any theory so far, if all of our checks show that it's a valid signal, then we'll say, this is a gravitational wave, figure out what it is.
Even if you don't know what it is.
Right. And
sure.
I think that's a really important feature of the instrument. We built it in such
Feature
a way
of
that we
the
think we can gain
instrument.
confidence with these two and then with others that will come
Yeah.
online.
So
Philosopher Chris
let's
Payne.
turn to the
I'd like
instrument.
to
Yeah.
amplify a little on that.
Yeah,
if you don't
please.
mind.
Go ahead.
Because that's really the interesting
We will
part.
move on at some point.
Yeah.
I assure you.
Feature of the instrument.
No, but that is really, what David is saying is really the heart of the interesting part of this. I mean, here we've opened a field and we call it gravitational wave astronomy.
Yeah.
And if we don't have something like what David is saying,
Sorry,
some
bud.
new things that we don't understand at all, it's not that the field is a failure, but it would defy all the prior history of advances in astronomy. Turns out every time you open some new field, you find something you didn't know.
Right.
And what David said, and we'll go back to that, we have
What?
all sorts of internal tests.
You find
within our
something you
own
didn't
experiment
know.
to establish that we, as best as we can, that we are looking at a gravitational wave and not something else. We should talk about that.
Well, that's what I'd like to turn to now, the actual
Yeah.
detection of these
Philosopher
waves.
Chris Payne, I'm
And
still
we're
black
going to,
hole.
again, begin with a little piece that
Black hole.
speaks
I'm
to
a black
the
hole.
earliest attempts by
Ah,
someone named
detection.
Joe Weber. Can we roll that video, please?
This is
Wow.
an artifact.
Wow.
It's one of the bars that Joe Weber used in the 1960s.
Bars.
Joe was the first person to take seriously as an experimentalist to try to actually make a detection of gravity waves.
A
What we
bar.
have here is a very large aluminum bar. The
Yep.
theory was that if a gravity wave comes by
Yep.
and space expands and contracts, if these were free aluminum atoms, they would just move with the local space. But they're not, because they're confined by bonds to other aluminum atoms. And so if you think for a moment of those bonds like little springs connecting all the atoms, when the space distorts, the atoms try to move with the space, but the springs hold them back, so that puts some tension in the springs. And after the wave went by, Weber's idea was that strain on those springs, that energy would be released as a sound wave in the bar. Joe was a controversial character, and
So it's
people
like me.
don't give a lot of credence to his claims that he had actually detected gravitational waves. But to me,
Where?
Joe is a hero because
Joe Weber?
even though he's a model of what not to do in data analysis, he was the person who had the chutzpah to go and make this first attempt. If it wasn't for that pioneering work, we might well not be here, and he did think of many of the ideas that we would later incorporate into our practice.
Very good. I appreciate you.
So,
I'll give you
Ray,
guys these
Barry,
ideas.
you were around when these experiments were going on. And what's your
Phosphor
view
Chris Payne.
of Joe Weber and this approach and the impact it had on how things developed?
Well, I mean, you really want it from me?
I am happy to have it from you, yes.
Look, in fact, it was the beginning of thinking about, at least in my life, of doing it interferometrically, doing it a different way. I'll tell you, I mean, it's a little bit of a story, and you're asking me, you should stop me when I've said too much, okay? But the thing is, I was asked as a young man to do something which you can do with your eyes closed, but I could not even do with my eyes wide open. And with every piece of my brain working properly, and that was to teach a course in relativity. Okay? I'm an experimenter, and I was asked to do that.
I'm teaching you
So
guys.
I was in 1967,
One-
68,
right.
at the time when
Oh,
Joe, not
no.
yet published, but there were news all over the
Phosphor
physics
Chris
community
Payne.
that he was detecting something.
I'm a black
But
hole.
he hadn't yet published his result. In 69 is when he published the result. So here I am, and not knowing tensor analysis, not that equation, and I loved what you did there, as you took this thing and unpacked it.
And this
it got
weed
more
has nothing to do with it.
Okay. I had to try to deal with that, okay?
I know you're
Never having
wrenching.
learned
I see
tensor
you
analysis.
wrenching at your soul.
So
You
anyway,
just-
so I can't tell my department chairman I don't know anything. I'm not allowed to do that.
Right.
So what comes of it is I teach this course as best as I can, and I get to this experiment. I can't explain it. In fact, the kids in the class asked me to say, what's Weber up to?
Yeah.
And the explanation that Fred Robb just gave, I couldn't have made that.
Are you
because
Joe
I didn't
Weber?
Understand. Here, I've been teaching a course where there is no more a gravitational force. It's gone.
Right.
It's
Yeah.
all in geometry.
Sorry,
And
dude.
here's this thing that requires a force again.
Yeah.
So I said,
Phosphor Chris Payne.
Come on.
I'm a
So
black
I sat
hole.
back and I tried to figure out how to explain
Chill.
how you would detect a gravitational wave to people in the most simple-minded way I could. I mean, with the the least amount of that formalism as possible. And the thought occurred to me in this course where I was sort of one day ahead of the students, if that. And I came up with the idea of the most elemental thing you could think of, which was, and this is why I tell you the story,
Water.
was like, why don't you throw some masses out there? Put them out in space.
Yep.
Hydrogen.
And put clocks on them.
Nitrogen.
Good clocks. I knew about you could make good clocks.
Gold.
But not as good as I needed. They were Gedanken clocks, okay? And so what happens is I said, let's time the light going from one clock en masse to the other.
Cobalt.
And then use that as a basis for looking if there's a
Zirconium.
gravitational wave or not. Because a gravitational wave, as it comes down on that system, will cause the time to change because there's the space between them is shrinking and expanding.
Yes.
And that's a very straightforward way of thinking about it. Not this molecular thing where you don't really know what the molecules are up to and everything like that. And I got the kids in the class to do this, a simple problem to do, and
Kids.
relatively just that problem. And I put it aside.
Who do you teach?
And now comes the connection to the question you asked me. Was, okay, in 69, he writes his paper, which was a stunning paper, by the way.
Okay.
And it caused at least 20 groups around the world to do and emulate that experiment because it was such an important result. And by 72, it was quite clear that most other people did not see anything.
Mm-hmm.
And the problem was not, I can't tell you exactly the reason why they didn't see anything. I mean, I can tell you the exact reason why they didn't see anything, but there's nothing to be seen. But I can't tell you what went wrong with Joe's experiment, okay?
Right.
I mean, I had a theory about that. I don't want to go, that's a waste of time right now. My guess is he was not a good enough experimenter. That's my guess, okay?
Joe?
I mean, he probably believed too quickly what he had, and he didn't do enough checks. That's my guess.
Right.
And
Probably.
well, let's leave it at that. You can ask me about that later.
Sure.
Sorry.
But on the other hand, what happened is
Joe,
that
you know him
triggered me
personally?
to think about, well, maybe this crazy idea, the Gedanken experiment, that I was thinking about in that course, maybe if you could make that into a practical experiment,
Right.
maybe because I didn't understand the thing in the first place,
Right.
maybe that would detect gravitational waves.
Wow.
And that's where, at least in my life, others had thought of it too, by the way.
Yeah.
I'm not
No.
the only one by a long shot. But that's how the thing evolved in my life, that we developed this.
I'm the
experiment.
black hole.
Yeah.
I could
can tell you.
understand every piece of it.
Gotcha.
You see?
And we'll get to actually
Yeah,
a version
yeah,
of that. But
yeah,
Barry, your
yeah.
view of those early days?
Yeah, Joe Weber first. I think I was really an outsider doing particle physics.
Yeah.
And I thought he was a one of the most imaginative, technical, creative guys.
Joe Weber.
And the dilemma for me is how he could be such a terrible scientist at the same time.
Philosopher
Which
Chris
I think
Payne.
he was. This wasn't the only time he thought he saw gravitational waves. It went through his career. He was embittered. And yet he made a tremendous impact. He had the insight how to build this stuff that we
And
never
he was never
thought about.
convinced that he didn't see them. Is that?
Yeah, because better experiments didn't.
But what was his view? I mean, I think he held to this perspective.
He felt he was being mistreated, and
Yeah.
we didn't understand, and we were against.
Well, it was even worse than that. Do you mind if I interrupt? Because
Sure.
I lived through it. I mean,
You speak on how they feel?
you were really doing physics, and I was screwing around. You know. But the thing that happened was that a very famous physicist, and I will blame it on, and give credit to Dick Darwin. Dick Darwin,
From
you
IBM.
probably know he was at IBM. Well, IBM.
I
and
know him from
Columbia.
IBM days.
Yeah, well, he
Yes.
was in it. That's exactly right.
Yeah,
But
right.
Dick Darwin.
he had free license at IBM to do what he wanted.
Darwin.
In fact, that's when IBM still had their labs here in New York, across the street from your guys.
Right.
You know, and so he and a guy named Levine, just as a sort of a pleasure for the afternoon, they decided they'd make a little tiny bar, just like what you saw, but a well-designed bar, well understood and well calculated.
Mm-hmm.
In other words, a lot of intelligence went into doing that design.
Yeah.
They did it, and they knew exactly how sensitive they were.
I know where I am right
So
now.
what happened is that the acrimony in this whole thing really happened because
I know exactly what I'm
Weber
doing.
and
Talking to
Darwin
you guys
would
about
meet
this
at
stuff.
meetings. Now this is now into the late 60s and early 70s, and they would meet, and Weber would give his most recent results.
Now what?
In this case, by the way, he became very serious with the results when he had 3 detectors. One in his lab in Maryland, another one in a golf course about 8 miles away from his lab, and then another one in Argonne Laboratory in Chicago.
Yeah.
And that's when he began to really say he's seen something, because he saw coincident pulses in all 3 of them, about 2 or 3 a day. Okay? And what happened is that Dick Darwin, who knew his apparatus
What?
much better than Joe Weber did,
2 or 3 a
unfortunately
day?
for Weber, and he could tell you how much sensitivity. You could go to Joe and say, how sensitive is your bar? And he couldn't really tell you. And I'll tell you how much we thought he was sensitive. 10 to the minus 16 was the very best it could have been in these units. And the first detection was at 10 to the minus 21, okay?
Right.
So it's many, many, many orders of magnitude away. But he didn't know that himself. And now his defense, when
Me?
Dick would get up and say at a meeting, I built this little thing, and I know exactly how much I see. I see nothing at the level of 10 to the minus 16. His response was not a rational response. It wasn't, well, I know my sensitivity, and I see something at 10 to the minus 17 or something like that, and you're not sensitive enough. That's not the response. The response he made is, you didn't do it the way I did it. And that was the wrong way to approach this whole problem.
Very
Okay.
interesting. Wow.
You weren't there.
I wasn't.
Who?
No. So
Okay,
let's think
Mr.
about the
Weber.
right way to do it.
10 to the
which, you
negative
guys have now
16,
achieved.
negative
So we've got
17.
some pictures. Tell us what we're looking at.
Are these like,
There.
That's 4-mile-long arms, 2 of
whoa.
them perpendicular to each other, and we send light from a laser, split it so it goes down both arms.
Whoa.
And comes back, and if the arms are equal length, we make them cancel each other.
The light cancels
The cancel.
against itself. And that's
Yeah.
how
We
to
have
think
a
about
photo
that.
of
Can
it.
you give us a way of thinking about it?
The light comes in a waveform, and as it goes down one arm and comes back, and goes down the other arm and comes back, we reverse one
Wow.
compared to the other, so that there's a black.
So like a peak and a trough are kind of
And then a
crossing
black
across
hole,
each
philosopher
other.
Chris
And
Payne.
it's black. And if one of the arms gets a little longer than the other one, they get out of time, and then we see light. And that's the simplest picture.
Wow.
Yeah, but we're going to
Precise.
try to do a version of it here, if you don't mind. And I've tried to do this experiment before. I've always been very nervous about whether it's going to work or not. I'm not the slightest bit nervous because I'm not doing it. One of you experts is going to do. Can you bring out this
no.
interferometer, if you will, from behind the stage?
Me?
So here we have
Is this me?
a slightly smaller version of what you just described.
Me?
So, I mean, I'm going to turn it on and then
No way.
ask one of you guys to explain what's actually happening here.
Oh.
Wow, we actually have some fringes. Can you get those up on the
Green.
screen? I should not be standing here. Nergis, would you do this and just take us
Is
through
that
what's
weed?
happening
What
there?
does the green color represent?
Okay, so it's an interferometer, and what we have here is a laser. It's actually a laser very
Can you
much
bring
like
the lights down a little bit over
like
here?
a laser pointer. And we have a mirror here that's a special mirror that takes half the light and lets it go through it, and the other half of the light gets reflected from the mirror. Oh, you know, in the old days when people smoked, you would just like light up a cigarette and make this all happen.
Yeah.
But,
Much more PC now.
Yeah.
This is bug spray, by the way.
No way, bug spray.
Good, it'll kill the roaches too. So
No
what
shit.
happens is the light
Kill
then
the
reflects
roaches.
off of these two mirrors and comes back to this beam splitter, and then just as Barry explained, if the peaks of the light line up with each other, the light in each arm, then you get a bright part of light on the screen, and in the places where the peaks line up with troughs, the two waves cancel and you get a dark fringe.
What
And
is
so
green?
What you can see as you go through looking at those, wherever you see dark stripes, those are regions of space where the peaks lined up with the troughs and the light beam canceled itself. And so our measurement in LIGO is pretty much just that, which is that
Wow.
we operate it under normal circumstances where we make the two light beams cancel each other, so it's dark.
That happens
and then when
right-
a gravitational wave comes by,
And then
it gets tiny bit
when I
brighter.
talk and then it-
and we can
still
measure
there.
that tiny
The
bit
black
brighter.
hole,
Now,
philosopher
that's one
Chris
of the things
Payne.
that's very interesting to see on this picture here.
Philosopher
The dark
Chris Payne.
Between the dark stripes and the bright stripes is about it's a fraction of the wavelength of the light. And so right here on this screen, you're seeing separations that are of order a fraction of a micron, so about 10 to the minus 6 meters. I'm trying to convert that into units that we understand. It's the spacing
Six is evil.
is a fraction of a hair of mine. So you can see right here on a
Hair
screen
of
with a
yours.
simple apparatus like this, and more or less with our eyes, in going between bright and dark, we are seeing differences of about, a fraction of my hair between these two arms.
Now, if
And-
you just hold still for 1 second, can we make
you're
this
holding
as
your
stable as we can? So everybody, please just hold your breath. Don't move. And we're getting relatively, my talking is now messing it up, so I'm going to talk really softly right here. But there you go. And then if a gravitational wave, obviously this is sensitive to all sorts of disturbances, not just gravitational waves, but
Right,
the
Brian.
point is, disturbance by yelling at it. Can you get this
Let's-
to move by?
Let's clap.
Thank you all very much for coming. It's been a very enjoyable day. Thank you very No, but there you go. So, and what you guys need to do, presumably, is to isolate your 4-kilometer long version so that when people clap or a tree falls or someone revs a motorcycle engine, it doesn't shake like this. So the only way that it will shake is if a gravitational wave rolls by.
Exactly.
And presumably that is the challenge. So thank you for this little demo
Whoa.
here.
Whoa.
So how do you do that? How do you isolate it in
Whoa.
such a way that the
You guys
only
don't
thing
know
that
how?
can make it shake are waves of gravity?
You guys don't know how?
David should let David tell
Yes.
you.
You
And I think
don't know
probably
how?
correct him if he's wrong.
One good thing to do is to think about the two challenges that we have in building this instrument. One is keeping these objects that are points in space-time that should only be influenced by the passing gravitational wave, keeping forces away from them so they're not moved by things like seismic noise. And then the other challenge is measuring
Seismic
with ever
noise.
better precision with light the distances between them. But so let's first talk about this problem of
Seismic
the masses
noise.
being disturbed by the outside influences. Clearly, seismic waves, and that could be from any source. It could be from the ocean pounding on the shores, which can be seen completely inland. It could be passing trucks and so forth and so on, wind shaking, people passing nearby. All of these things cause the ground to move. And
Yep.
we want to keep that motion from getting to the points in space-time that we use to watch the gravitational
What's
wave.
an earthquake?
And the basic principle we use is pendulums. If you have a pendulum,
Pendulum.
let's imagine it's about this long, and it swings at about this rate, about a half a second per cycle. If I move the top
Half a
support
second.
slowly compared with
Whoa.
that frequency, the pendulum will just follow. But if I move that top and I shake it at high frequencies higher than the pendulum frequency, this mass is going to want to sit still. It has
So I'm a
inertia.
pendulum.
It naturally wants to be an isolator for frequencies higher than this pendulation frequency.
So
if you put a
I'm
bunch of these things
still
in
black hole
series,
phosphor
which is what we
crisping.
do in advanced LIGO, here you see an image of the bottom of one of these multiple pendulum suspensions, then each layer acts like another filter against the seismic noise, and the system wants to stay still in inertial space, and that's exactly what we want.
That's
we
what
also
I'm
use
doing.
more sophisticated systems where, for instance, we put an electrical sensor next to one of these intermediate pendulums and measure how the outside cage is moving with respect to the pendulum. It generates an electrical signal into an amplifier and then into a motor where we tell that motion to stop. So
Outside cage.
Stable platform. So through this process of
Stable
multiple layers
platform.
of isolation, basically using the pendulum idea in different ways, we can suppress the seismic noise by 10 to the 12 orders of magnitude or something, so incredible amount, and get to the point where, in fact, the mirrors are moving far less due to seismic motion than they would be moving due to a passive gravitational wave.
Wow.
It's not our only problem. The next thing that happens is that we have to deal with Brownian noise. These mirrors, like everything, is in equal heat bath. Each one of the modes of the optical system's got energy, thermal energy. You've probably heard of Brownian motion, which causes, for instance, the needles of a very fine electrometer to shake around. These things move in the same sort of way, and to manage that, we have to use materials with very, very low mechanical losses, gather that energy into very narrow peaks that are outside of the region and frequency where we're trying to do the measurement. So a lot of it is very fine machine making to get good instruments with very low mechanical mass and very, very, very small motion.
Now, you did this in 2 steps, right? I mean, there is LIGO and then advanced LIGO. So the first one was what, 2?
Trying. Sorry, buddy. Hope you don't mind. Still in my black hole. Still can't argue it. But I'm listening. Appreciate you guys' time.
2002 to 2010, it was operational, roughly. Is that right?
Yeah.
And
2008.
Yeah,
2008, and then you
2010.
went offline for the upgrade.
Yep, offline.
But
I
it
went
wasn't an
offline.
unexpected upgrade. This was your
But the
plan
upgrade's
from the
right now.
get-go. And that's a kind of forethought that is wonderful. But why
Forethought.
did you think of it in a two-stage system? Why not just go for the one that would work from the outset?
Well, that's almost really part of the whole business of how the project went from tabletop to being
Good,
a
yeah.
large scale. And I like Barry to talk about it, but let me give you the philosophy we had. And in fact, it succeeded exceedingly well. The
About
philosophy
what?
was indeed what you say. Once we got to the point where we want to write a proposal for the large system, which was done in 1989, and that's when the real proposal was written. Prior to that, there had been
8.0.
studies of
And
large
God is
systems
9.
and how much they cost. That was earlier. But the real proposal for this was written in 89 with exactly the strategy you described. And the reason we did that is because you wanted to at least...
Phosphorus paint.
This is an expensive project.
What are you
People
doing?
were skeptical of the whole concept to begin with, so you had to be very, very careful. What were they really skeptical of? I'll be honest with you. The skepticism was the calculations that Kip had done and all of the people had done about gravitational wave sources.
Kip Thorne.
Kip
Yep.
Thorne, right,
Yep.
yeah. That was considered flaky. The whole idea of being able to do measurements at 10 to the minus 18 meters.
Kip.
You need to do to get to 10 to the minus 21 planes, even over
Kip.
4 kilometers. That was considered way flaky. I mean, most engineers, when they hear about 10 to the minus 21, they think you're out of your mind.
Go back
there's
to Kip.
nothing you do to 10 to the minus 21.
Me and Kip
And
got a
10 to the minus
fun.
1 is a fractional stretching of the length
Yeah,
that you're doing.
or let's
your-
make it
yeah.
simple. Let's say over
Yeah.
4 kilometers, it's the motion of the mirrors is 10 to the minus 18 meters.
4 kilometers.
Should I
And just to put that in the context,
Yeah, yeah.
how do we think about 10
Yeah.
to the minus 18
let me
meters?
quickly say
Yeah.
that. I mean, it's an easy way. Well, I think we should, I'll do what I did once before. You start with a meter and you say, okay, let's divide that by 1,000,000 3 times, 3 times over, okay?
Yeah.
So you start with a meter, okay? And then you say, let's divide by 1,000,000, and we can still sort of imagine that.
3.
And what are you at? You're at 1 micron, which is about 1/130th the size of your hair. That's still imaginable. You can-
130. Wow. Yeah. No way.
Then you divide by another 1,000,000. Okay, you're at 10 to the minus
Boltzmann's
12.
brain.
And that's smaller than an atom. An atom is 10 to the minus 10 or so in these units. And
Including the electron
Yeah,
cloud.
you're
Yeah,
just,
not the
you're,
nucleus,
you're sort of in the atom,
Yep.
but you're not yet to the nucleus.
Good,
The nucleus
yeah.
is miles away yet.
Yep.
And now you divide by another 10 to the 6. And now you're 10 to the minus 18. And now you're in Never Never Land. I mean, most people just can't imagine that. I mean,
No, you're not.
down to the point where you're deep inside the nucleus.
So it's like 1,000th the
the
size
size
of
of
an
a nucleus. So,
Right.
that's
Phosphor
the best I
Chris
can do
Payne.
for you right here. on
Yeah,
the
that
spot.
works.
Okay.
That worked for you guys? I think it's very good, right?
And the people thought you were kind of crazy,
Yeah.
that you would even be able to do such a thing. So we had
No, I'm not.
multiple things that we had to do. So we had to be very, very careful.
Thought who's crazy?
And in that proposal, that's why we did it this way. We wanted to take, many people had built prototype detectors on a tabletop, and had demonstrated independently
Crazy?
various techniques. For example, the kinds of things David just talked about.
Yeah.
Good vibration isolation systems. Then the ability
Good
to
vibration
read with a light
oscillation
and
systems?
spectrometer. You don't have to build a huge thing to read 10 to the minus 18 meters. You can do that all in a little instrument. You're not measuring a strain of 10 to the minus 21. Then. See, for gravitational waves, you have to make it bigger. But you can certainly prove in a little instrument, smaller tabletop
I see.
instrument,
And that's
that you
where-
can measure 10 to the minus 18 meters. And that took a while, but people were getting there. Okay? So.
And what year is that? What do you...
Oh, no, 10 to the minus 18 is an exaggeration. 10 to the minus 16 certainly we could do in those days. Okay? And that was, we're now talking about, a lot of people worked on that. Very good German groups,
a group in Munich worked on it. And they did much of the initial development of this thing. And then the group in Glasgow, and then the group at Caltech, and the group at MIT.
Glasgow? Whoa, no way, what?
And with that development,
Robbie
you could say to
Vaughn?
somebody who was a real critic, look, we're not miles away from doing this, the individual pieces that you needed. We could do the vibration isolation. You could do the sensing, okay?
Whoa.
And now the question is, we can't do the measurement that's a scientific measurement unless we take that whole thing and put it into something that's very large. And that's when
Facts.
the money has to be spent.
Yes.
So you knew, and what we traded on was the fact that you had done these things in the prototypes, the things that people were skeptical of, and that the new thing would be that you had to now build it on a large scale.
Yep.
And so we wanted to promise no more than what we had done in the laboratories.
Who's we at CERN?
And that's why we made two different things.
Two
Because
phases,
It's two-stage system.
Yeah.
Because what we had to develop in the laboratory was probably not good enough for some of the more reasonable sources. They were good enough for some of the wild sources that Kip could think of, but they weren't for the more reasonable sources. For example, we couldn't do a neutron star binary.
No, I'm reasonable.
Yeah.
Right.
Okay. Unless it was very close, and that was unlikely. Okay. So consequently, we did right then and there.
Einstein was close.
This is a technology development, but has a
To
chance,
what?
not zero chance of detecting something, but we were not very high probability. for it.
Detecting
But
what?
we
What are
said,
you trying to
we have a
detect?
second piece to this, and now here's a critical thing. You've got to build these facilities big enough so they can encompass both the first version and the next version. And that's where all
Facilities.
the money was going. In other words, all the money was going into making buildings, making vacuum systems that were 4 kilometers big.
And how much money are we talking about?
We're talking about that, about 200 million by this time. Now, Barry can tell better, but I think that's about right.
Barry.
Well, up to now, 1 billion.
Yeah, but no, at that time, I mean, just for the construction of the facilities.
Right.
And the thing is that
You
then
you
we
guys want
said,
to put $1
look, we
billion
don't have to
into
change
this?
those
Into
facilities
me?
to put the better detector into it. So that was the initial investment, was good for both the things we knew how to do at that time and also for what we thought we would do. But we didn't have to change the vacuum system. Everything would work. The expensive part of the thing, you would have to put another something, what would be the equivalent of another detector, but you wouldn't have to build the infrastructure. Okay?
No.
That was the proposal.
And that went through.
And that eventually went through. Yeah.
And, Barry, I don't want to embarrass you, but everybody that I talk to says that you were the guy who made this happen, right? I mean, there was the vision, there was the plan, but that you're the guy that made this happen. What would you say was the big challenge and the big thing that needed to
Well, I don't
be
think
done?
we're successful. I mean, we're successful in doing the science, but I must say, I never know of anyone that thought this was going to take us 22 years. It's 1994, and our first detection is 22 years later. And I don't know whether you or anyone thought it was going to take 22 years. but I think probably
1994.
Most of us felt these
Phosphor
things
Chris
would be
Payne.
half that. So we're not as
That's
good
my
as-
birthday.
Did you lose hope as you were doing this at all?
No, we're just not as good as we thought we were, I think.
So you just gained humility through the process.
So when you point and say, we did it, or I did it, or something, I think we're...
I want to give him credit. I mean, if he won't do it, I want to do it.
Please do.
Because I've lived through this too. Look, we were pretty disorganized. Okay? I mean, that's why it's so important to transition from the tabletop
Barry, you got me.
version of this thing to what we call the LIGO full-scale thing. Okay? It's true that we had begun by the middle 80s to begin, or early 80s, to look at
Whoever's on the end, I forgot. He made a good body
with
language.
industry to see how much it might cost, how you would make a bigger detector than the little tabletop things we had. And we did a study of it. In fact, became the basis for two things. It became the basis for a presentation to the NSF jointly by Caltech and MIT together to push the idea that you should build a big one. And we had a lot of help within the NSF, by the way. People in the NSF thought this was exactly what the NSF should be doing. I'm glad they thought that way.
Rich Isaacson?
Rich Isaacson.
NSF.
And he then
Rich-
made the investment in the NSF, the intellectual investment.
Isaacson.
And showing the people in the NSF this was a good thing for them to do. Because it was risky, but it was also, if it worked, it had a tremendous payoff. And that's pretty, I think and that's, I think, an honest statement of what was going on. And so what happened then was that, okay, we were able to get this collaboration going.
Yeah.
But it turns out the principles were not, that includes myself and Ron Griever, who unfortunately not here right now.
Phosphor Chris
and
Payne.
Kip Thorne. We were the ones who on it. Well, we were not necessarily
You and
the
me,
most
we
strategic
know.
thinkers, I'll be honest with you. And in fact, we squabbled with each other, not several of us did.
Joe
And
Weber?
What happened is that, in fact, in 1986, when NSF had started looking at this whole thing, again, Richard Garwin played a very important role in it at that time. He wrote a letter to the NSF, says, look, he's heard about this thing. You know, why he was so important is because of the experience he had with Weber, okay? But he was honest in his thing, by the way. It wasn't totally critical.
National Science Foundation.
He was critical, but also he was trying to
Holy
help. He said,
shit.
look, if you're going to do this, he said to the head of the physics branch of NSF, if you're going to do this, you ought to have a summer study about it. A study with people who are not in the field. Let them judge this. And that was put together, and we got some very good people doing it, people who are not in the field, Nobel Prize winners who were experimenters, many of them, a lot of people now in the field, but who were not in the field then. And they gave an enormous endorsement to this.
Huh?
The endorsement was, don't mess around, build 2 big facilities right away. Build them right away. Why? Don't make any more prototypes.
Right.
If you want to know, you got to get to the science, and you got to find out what are the problems when you make this bigger. And they sort of recognized that, and they also said, don't build just 1 because they want to see the science of it.
Sure.
You want to have 2. So they saw that right away. That was part of the strategy. And we hadn't yet written the proposal. You see, all of this gets incorporated later in 1989 in the proposal. But the thing that they were very skeptical of was, look, here was this 3 of us who were not adept at running things. We couldn't quite agree on things, among other things. And they said, get yourself a single director. And that was bingo. No, that wasn't him right away.
Well, when are we going to get to Barry?
Yeah, we're getting to Barry. We're going to get to
I'm on the edge of my seat here.
We're going to get to Barry. First, there was a fellow named Robbie Vogt who helped us write that proposal. And then it became
Felony
Barry.
Robbie Volt.
Okay, and Barry really pushed it through.
Barry. Lost for Chris Payne.
I actually think the key to success is one that people don't really point to. And this was something that was very hard to sell to the NSF. But it wasn't just building this big thing. The NSF actually supported us. That as we built this and finished building it, we were able to concentrate on all the stuff that David talks about. That rather than the usual thing, when you build a big thing, is they take away all the money or the work that you do in your labs to develop all the things we don't know how to do, and come back after you either fail or succeed. And they kept us funded to do all the work toward the second generation in 1998, 1999, when we finished this.
But you insisted on it.
I insisted on it.
Yeah, no, that stability
I
is
thought we
critical,
would never
of
get
course.
to the second step without that.
Right.
But they bought off on it, and that to me was the key to success, not any little individual piece.
Right. We're starting to run a little short on time. I want to get to our final section, which is just looking toward the future, right? We're going to also begin this with a little final clip. If you can run that, please.
In the era when we were trying to convince people that LIGO should be built, for me, this was the most exciting thing, is the likelihood that we will see waves from phenomena that we had never dreamed of.
No way.
After all, every time a new window has been opened on the universe, unexpected things have been seen, and this will surely not be an exception. Gravitational waves are the only form of radiation that is so penetrating that it would travel unscathed through the very, very hot and dense material in the earliest fraction of a second of the life of the universe.
Wow.
So if we are ever going to actually see the Big Bang, the only way we will actually see it is through gravitational waves. I therefore regard the ultimate holy grail of gravitational wave astronomy as probing the Big Bang. Some of the strings from which everything is made, fundamental strings we call them, which are submicroscopic, far smaller than the size of an atom or an atomic nucleus, that some of these strings are expanded to cosmic size by inflation. And there are calculations using tentative versions of string theory that show that this may be the case. If that happens, the result then are what we call cosmic strings. And these cosmic strings are simple enough that we can predict with high confidence the shapes of the gravitational waves that are produced when 2 such cosmic strings collide pass through each other and with high probability recombine, so you wind up with two strings that have kinks on themselves.
Right.
And those kinks then travel down the strings at the speed of light, emitting gravitational waves.
Whoa.
The resulting waveforms are very well understood.
I get it.
Are quite simple.
You're beating it in the
And
bush,
the
Kip.
estimates of the strengths of those waves are such that LIGO has a real shot at seeing them.
You're talking to me.
So I love the fact that he speaks of string theory as if it's absolutely right, which is sort of a beautiful thing for somebody like me. But he really means
Philosopher Chris Payne,
if
Brian
string
Green, what
theory
up?
is correct, that there's a chance that we could see the evidence of strings through these gravitational waves that undulating strings would create. But you know, we don't have a lot of time left. But
Yeah, right.
starting with you, David, when you
Wow.
think to the future, you know, both in terms of the devices and the things that we might find, what gets you most excited?
Well, I think there are two directions we can go to go well beyond advanced LIGO. And well beyond probably makes, from initial LIGO to advanced LIGO was a factor of 10 in sensitivity. Because we look at the amplitude of the waves, being able to reach out a factor of 10 times further brings 1,000 times as many possible sources into our reach. Probably the next step would be another factor of 10 on ground.
Wow.
And there are a couple of different ideas of how to do that. I mentioned that one of the limits to what we can see is the thermal noise, and one thing you can do is refrigerate the masses down to a fraction of a Kelvin, or maybe something not quite as cold to reduce the thermal noise. Another way
Kelvin.
you can do it, this is a strain in space. If you have a meter stick, it will change by 10 to the minus 21 meters when the wave goes by. If you have a 10-meter stick,
Yep.
it will change by 10 to the minus 20, 10 times more. So we
Okay.
have 4-kilometer-long arms to take advantage of that now.
Right.
If we had, say, 40-kilometer-long arms, that would make the signal 10 times bigger without any of our noise sources
Right.
growing that by that same amount.
Right.
So there are a couple of ideas that we have for how we could grow ground-based interferometers into systems that could reach even further back and, say, get to the point where we could see the very first black holes, see the first black holes in the universe. I think, though, the other thing, there was an image up on the screen a little while ago of a constellation of satellites in space. It's obvious that that's an experiment that must be done. It
Philosopher
would
Chris
probe
Payne.
not the same frequency range of gravitational waves.
I'm a
so it's
black
a little
hole.
bit like the difference between radio astronomy and optical astronomy. But it would be also a place where you could, instead of having a mere 40-kilometer-long arm, you could have 1,000,000-kilometer-long arms and have a signal that is that much larger and be able to probe with incredible precision the waveform of the gravitational waves, use small black holes orbiting around big black holes as a way of
Wow.
mapping out the curvature of space-time in more detail.
Right.
It's an experiment which must be done. And we think we understand how to do it, and I think we're getting closer to the point where we know, have a good date for sending something like a LISA, a gravitational wave antenna. Into
And the
space.
Europeans are pushing this somewhat more than we are.
Well, there's a bit of an unhappy history there. For a while, there was a really good joint mission between the U.S. and Europe, and the technology was working along well. The James Webb Space Telescope got much, much more expensive than anyone thought. And the way the walls work for money in NASA is that if there's one space experiment that's in trouble in science, it eats all of the other ones up.
Yep.
And that caused us to break a number of relationships that we had with the Europeans to build space missions, and this was one of them. So the Europeans have gone ahead, and they actually have a date of 2034 for a launch of a space-based mission. They'd actually like to bring that in a bit, and their calculations for technical readiness say 2029, 2030. Yep. The U.S. has got a small effort that we're trying to catch up with them in the sense that we're at least going to play a minority partner in it, and to participate in this really wonderful experiment. Maybe we can even grow our own participation based on the successes of LIGO. And also a recent experiment, a test experiment, was put up by the Europeans called LISA Pathfinder. And while the data are not yet publicly released, I think we'll see that it performed really remarkably well. So it's on its way. It's still a ways away.
So Franz, what about the future of the numerical methods? Do you see that playing as a vital role going forward? New templates, new ideas in that domain?
Yeah, and in particular, if we think of now adding neutron stars to the mix. So we're going to hopefully learn a lot about black holes in the universe with upcoming observations, other events. But in terms of the templates, we pretty much have that under control.
Franz.
But the one thing which we don't have under control is neutron stars.
Nope.
And you have the Einstein equations, the
Whoa.
geometric side, the G on the left-hand side, and the T mu nu, which is the matter on the right-hand side, With black holes, that's zero. We just said that they're zero. We don't worry about matter. It's purely vacuum.
Yeah.
Neutron stars now, of course, they made of matter. And the thing that's
Huh?
both interesting and
Made
challenging
of?
about it is matter in those extreme conditions, the density of neutron stars, so essentially the gravitational force is so strong that
Made
packs
of?
all of the neutrons together in basically one big atom with the mass of the sun. So for example, if you compress the Earth down to those densities, it would be about the size of a football field. So incredibly dense matter, we don't understand those properties. And so when to try to solve what the gravitational waves would look like, especially when, say, two neutron stars collide, they form a hypermassive neutron star, they might collapse to a black hole. If a black hole rips a neutron star apart, we need to model that right-hand side.
Right.
And sort of interesting with the Einstein equation, so we use the words modeling and simulation.
Okay.
But with the left-hand side, the geometry, we're actually not modeling anything. We're actually solving Einstein's equations. There's some numerical error, but it's actually solving those exact equations. The corresponding equations for neutron star matter, that's the fundamental laws of particle physics, quantum electrodynamics, quantum chromodynamics, electromagnetism. There's no way in hell we can ever solve those equations in the same way that we do the Einstein equation. So we have to, now in the real sense of the word modeling, come up with an approximation for those things. And
Approximation?
because we
Who's
don't
we?
understand matter
What
at
did you
those
do? Is that
densities,
what
the
you do?
models are
You
incredibly
approximate?
crude, basically blobs of fluid. So the two things that are interesting about neutron stars, one is just when they collide, they're going to emit photons. And so we'll hopefully see both gravitational waves, perhaps a gamma ray burst, perhaps these interesting things called kilonova, which might be what's
Kilonova.
responsible for all the gold and platinum and all the bling in the universe, as opposed to stars which produce the ordinary stuff that make us exist.
Kilonova.
So there'll be a lot of interesting information that would come from the electromagnetic signatures, but also that will tell us really what matter is doing at those extreme densities. Yep. So there might be clues not just to
Whoa.
what happens with the populations of neutron stars and black holes, but it might be telling us something about matter at densities that we can probe in laboratories.
You're a neutron
So
star
that's
and I'm
very
a black
exciting
hole.
thing
What up?
Going forward with simulations.
And Nergis, is gravitational
Philosopher
waves
Chris
going to be
Payne.
your focus going forward for?
Yeah, I think so. So like one thing that we, there's an L in LIGO and there's an L in LISA, and that's the laser. The laser light
Looted.
is our meter stick, and laser light is light is quantum. It's made up of photons, and the quantization of the light is a big problem. It's a limitation to how well we can build future detectors. So for me, that's an area that I'm really interested in, is how do you engineer quantum states of light that can help you do better, and we're doing that in our
Philosopher
labs
Chris
now.
Payne.
And so yes, there's
Oh, black
plenty
hole.
to do. And for me personally, the field is just begun. We're filled with ideas, and now we just have to go build better instruments.
Very good. How about
It
you
just
two
begun,
guys, young
wow.
gentlemen? What are you thinking about for the?
How
For me,
good
I
of you
think
for tuning
we've,
in. That's your relativity.
Opened a whole new area of observation, and I can't imagine that we
Barry,
know
what
all
up?
the things we're looking for, and so we're going to be surprised. And I'm looking for the big surprises. I
Okay.
lived through that in particle physics when, in 1975, we found a totally new set of particles and a new way to see things, and I think the same thing will repeat itself here.
Ray, you want to take us out on a final thought?
Well, I'll give you the same thought that Kip had. I'll just amplify
Yeah,
what
sure.
Kip said something very important. He said that this field is
Ray.
fundamentally different in astronomy than what we now know, except for neutrino astronomy.
He's a
That
ray of
is
light.
closer to us. But
Except
in
the
electromagnetic
neutrino. I'm the
astronomy,
neutrino, yeah.
We're dealing with things that scatter.
Describe
The thing
neutrinos.
that
That
you
shit's
see
amazing.
has come out of a source. It isn't what actually went on deep inside the source. You're seeing something that has been bounced around by all the processes that are going on in the source. For example, when you look at the sun, you can't see the inside of the sun. Why? Because the light has been scattered so often. And the thing is,
It's
that
a black hole. It
takes
turns
a
black.
long time
I've actually
for it
stared
to
at the
come to
sun.
fills out through all of that stuff.
I've stared
So
at the
it turns
sun.
out that the idea that you are
turns
looking
black.
now at the dynamics of things, deep inside of the astrophysical system,
Stare at
we see
me.
only the outside
Turns
of it,
black.
says to me that we're going to learn an incredible amount of new things.
Philosopher
It's gonna
Chris
make
Payne.
I think it's going to make a change, a vast change, just in the way people look at astronomy. I'm hoping also, and this is now a faint hope, because I've worked in other areas, eventually I'd like to see this really have an impact on cosmology. And I think if we build the bigger systems that we're talking about, we will do some kinds of cosmology. We might be able to do the cosmic metric better, for example, to measure the same things that see with light. You see now, you might have a different set of systematic problems that might be able to help out where we're now not knowing things well enough. I wish we could see the Big Bang. I don't think this instrument, I know this instrument won't do it. There are very fancy ideas on paper that allow you maybe to do this. I hope the people at the CMB, the people who did the BICEP, will get there first, because then we'll really know something in my lifetime.
Well, when you guys get there, we will invite you all back for another conversation. So this has been a fascinating discussion. Everybody join me in congratulating the team for this fantastic achievement.
Appreciate it.
So, thank you.
Mental floss. Your name. Time Warner Cable? Hooper.
Hello. Today we're going to be looking at black holes.
And Hawking
we'll be covering
radiation.
issues
And
such as
entropy.
the escape velocity, the Schwarzschild radius,
So my ability
the
to
energy,
talk.
the mass, the temperature, and the entropy.
A restream ad popped up.
Terry been here for Fake Mike, Real News, Auditing America, Chase from the Allen Report, Auditing America. Welcome to Auditing America, folks. Thank you guys for tuning in. Please get this feed out, like, share, and subscribe. We've been putting a lot of work in, and we've been putting a lot of videos in the last few days, so we wanted to talk to you about some of the things that we've been through, some of the things that you haven't seen behind the scenes. Legalize freedom. We are not the real heroes. We're just doing our part
Legalize freedom. That's what I'm doing.
in history that Joe Biden got. Thank you very much, Brandon. There's no way that Joe Biden got the most votes in history.
Oh
but the
my
real
gosh.
fraud.
Oh, Joe Biden, are you serious? Don't get me started. Hyperspace. Cool. Is this Brian?
Good evening. Good evening, I'm Brian Greene. In April 1919,
Did you dye your hair?
a 34-year-old German mathematician was in his study, sitting at his desk. His 9-year-old son was on the couch, where he'd often be when his dad was working. And Theodor Kaluza was there at his desk, doing calculations as he often would, when all of a sudden, he opened his eyes wide.
Of you?
He slammed the desk with his hands. He shot to his feet.
And you're in the
and he began to
hyperspace.
sing an aria from Figaro. Dum dum da da dum dum.
What? Who's this guy? Philosopher
The
Chris
program
Payne.
here tonight will explore
Philosopher
what it
Chris
was
Payne
that Theodor
and
Kaluza
me being a black hole.
was singing about. He had found the possibility that there was reason to believe that our universe might have more than the 3 dimensions
Yep.
of everyday
I made a song and I
know
mentioned
about.
being
The
in
program that we'll be
hyperspace.
discussing here tonight will follow the variations on that theme that have rippled through physics over
Rippled
the
through
last
physics.
8 decades, and we'll
KPN
discuss
8.0.
where our thinking is today on this possibility of more dimensions than
Wow.
meet the eye.
Okay.
Now,
No way.
to give you a sense of where this idea came from, where
Right.
Kaluza's thinking came
Holy
from, we need to take a step back
He did say 8
and think
decades.
about certain physics, certain
KPN
discoveries
8.0.
due to Albert Einstein that were the precursor to Kaluza's thinking. To do that, we need to think back to roughly the year 1907.
No way.
1907 was a time when Einstein was really basking in the glow of having
I was.
already discovered what we call the
7.0, I was
special
really
theory of
looking at it.
relativity, material that we'll touch on a
It's
little
all
later
relative.
tonight. Various insights into nature of space and time.
Nature
and
of
he
space and time.
set
Me
himself
speaking
around
to you
that
right now, a
time
little
the
bit
goal
overriding you
of
sometimes, sorry, bud.
understanding an even bigger mystery, the force of gravity. Now you need to
yeah.
know, around 1907, and in fact way before that, many physicists believed
You
that
guys
gravity was pretty much understood from the work of Isaac Newton. However,
No.
Einstein was, of course, the
Not at
kind
all.
of thinker for whom there was no such thing as received wisdom that he wasn't willing to challenge,
And
willing to
Isaac
think
Newton
through
wasn't that?
in fresh, new ways. And in particular, when he was thinking about
What?
the force of gravity that everybody
What are you
was
doing,
aware of
Brian?
and thought that we understood well, he asked a very simple and basic
What are
question
you doing?
that no one seemed to have the answer to. And that question was, how does gravity really work?
I mean, yeah.
How
who
is it
put on
that
your
one
clothes?
object in the universe,
Who
like
put
the
on your
sun,
outfit?
can somehow exert a pull on another object like the earth, even though there's nothing
You know what you're
connecting them?
doing?
There's effectively empty space between them.
Ugh.
How does gravity get the job done?
Well-
So naturally, to try to
You gotta wear
answer
suits
that
and
question,
talk.
Einstein went to the Principia, Newton's Principia, which has all the results in math and
Principia.
physics that Newton found in his lifetime. You know, it was the book that was required reading for tonight's discussion.
The
In,
book.
of course, the original Latin. Now,
The
of course,
original
most of
Latin.
you therefore know the story, but for the one or two who maybe didn't quite finish the reading, let me just carry on. So Einstein went over
continue
to
the
Principia.
reading.
He opens it up to
No.
letter G.
You can go back
finds
and
the
look.
law of gravity that Newton had written down in the late 1600s. And then he goes a little further to the subheading M for the mechanism by which gravity operates. And there Einstein finds something surprising because
Philosopher Chris
Newton
Payne.
basically says, I don't know how gravity works. I've been able to write down an equation that
says
seems
this?
to govern its influence. But if you ask me how it actually gets the job done, I don't know. In fact, in his own words, he said, to the answer of that important question, the mechanism by which gravity operates, Newton said, I leave it to the consideration of the reader. Most readers at that point would simply read on. Here is where Einstein was different. He spent 10 long years trying to figure out how gravity works, and he finally did come to the answer with his so-called general theory of relativity.
Philosopher
and let me
Chris
just quickly
Payne.
describe to you what he found, because it sets the stage for this idea of there possibly being more than 3 dimensions of space. How does it go? What's Einstein's idea? Well, the idea is often described.
Yep. Sorry, dude.